The universe doesn't end with a bang, it ends with a whisper. Stars gone dark, atoms unravelling, even black holes fading into nothing. But in that final frozen silence, one idea claims the ending can be erased. When everything is finally dead and light has nowhere left to go, could spacetime itself reshape the ashes into a new Big Bang? Picture a cosmos so old that distance loses meaning, and history thins into pure geometry. In that austere silence, a radical proposal appears, not as myth, but as mathematics. We are used to endings that leave wreckage, debris to sift, ruins to date, a last scene to remember. But the far future may offer something stranger. Not a final event, but a limit where ordinary descriptions stop applying. In that limit, the universe does not simply grow empty, it grows scaleless. When no stable bound systems remain, the very tools of measurement, clocks, rulers, and the rhythms that anchor before and after can become impossible to define. That is where Roger Penrose begins his wager, an idea called conformal cyclic cosmology. It asks whether the deepest future can be re-expressed through a change of geometric perspective, as the kind of beginning we once thought belonged only to the past. This documentary follows the question where it becomes uncomfortable. If expansion and entropy drive the cosmos toward uniformity, why did the early universe appear so smooth, so low in gravitational disorder, and so precisely poised for structure to form? We will walk through the mainstream forecast with no shortcuts. Accelerated expansion, fading gradients, and the slow exile of galaxies beyond each other's horizons. We will linger where the last reservoirs of complexity persist, and where even temperature becomes a word without a practical instrument. Then we turn to the heart of the mystery: light. Massless particles trace paths that do not carry proper time, and a universe dominated by them may have no preferred scale at all. Penrose claims that this scale-free simplicity is not merely poetic, it is a symmetry. In conformal geometry, angles and causal structure survive rescaling, while absolute size evaporates like an unneeded coordinate. If that symmetry truly governs the final state, an astonishing move becomes thinkable. The infinite future of one cosmic era can be compressed to a boundary, and that boundary can be matched to a new origin. But elegant mathematics is not an ending, evidence is. The cosmos has left as a backlight the microwave afterglow so uniform that its tiny imperfections became a map of everything that followed. Conformal cyclic cosmology suggests that this sky might also contain faint scars from an earlier era, subtle patterns that would not be expected if our beginning was the first of its kind. We will examine those claims with the discipline they demand, because the microwave sky is a battlefield of statistics. Foregrounds must be stripped away, pipelines must be tested, and coincidences must be separated from predictions. And beyond observation lies a deeper obstacle: black holes, quantum fields, and the fate of information. Hawking radiation makes horizons evaporate, but the last stages press against quantum gravity, where certainty becomes expensive. So our journey is not a promise of a cycle, and not a sermon against one. It is an investigation into what after could mean when time depends on mass, and when geometry may be the only thing left that still counts. By the end, the question will feel less like science fiction, and more like a mirror held to our assumptions. If the universe can be described without scale, then perhaps the boundary between conclusion and origin is thinner than intuition allows. One fact remains, whatever answer survives. Our cosmology is a story written in light, and in the farthest chapters, light may be all that remains to write with. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We begin at the edge of the last usable energy, then trace entropy's logic toward a scale-free future where clocks fail. From there, we return to the first dawn and finally to the microwave sky, where any echo of a previous era must either appear or vanish under scrutiny. Imagine a time so far ahead that every familiar landmark of the cosmos has expired. Not just civilizations, not just planets, but the engines that make structure possible: stars, gradients, and the steady flow of usable energy. Cosmology calls this destination heat death, and it is less an explosion than a quiet arithmetic. Entropy rises, free energy falls, and the universe approaches a state where nothing useful can happen. In that far horizon, drama is replaced by bookkeeping, and the numbers drift toward equilibrium. Heat death is not a poetic phrase, it is the thermodynamic end state of an expanding universe that keeps mixing and thinning, while gravity slowly runs out of new ways to clump matter. Maximum entropy means the remaining energy is spread too evenly to drive work. Minimal free energy means no gradients remain to power stars, chemistry, or memory, because every difference that once mattered has been diluted away. The cosmos becomes dominated by thin radiation and inert matter, drifting through an ever larger spacetime. Even cold becomes a subtle word here, because temperature is not just low, it is irrelevant to doing anything. Endings matter in cosmology because they test what our laws actually mean. A theory that explains beginnings but cannot follow the future is incomplete, especially when the future is a long, clean extrapolation of known physics. The universe is our only laboratory at the largest scale, and its fate is a prediction we can compare across models, parameters, and assumptions. The stakes are not personal survival. The stakes are whether time, causality, and geometry keep their meaning when the last sources of order are gone. When the universe becomes almost featureless, we learn which parts of our descriptions were essential, and which were merely convenient. The standard story begins with abundance and ends with exhaustion, and it does so in stages that are slow enough to feel almost timeless. In the near future, star formation slows as galaxies run out of cold gas, and as feedback from earlier generations heats what remains. The brightest, shortest lived stars vanish first, and the sky becomes redder and dimmer as long-lived, cooler stars dominate. Over trillions of years, stellar nurseries shut down, and galaxies stop making new light, because the raw material for fusion is either locked away or too diffuse. What remains are long-lived dwarf stars, stellar remnants, and the slow rearrangement of orbits, as gravity keeps shuffling the same pieces. Visually, the change is not a sudden blackout. Spiral arms lose their glittering blue knots, and the bright, dusty lanes that once marked starbirth fade into a smoother, older glow. Clusters that once looked like cities of fire become suburbs of embers, with wide, dark gaps between them. The universe still contains stars, but it contains fewer reasons for anything to change quickly. Time stretches, and the sky's palette shifts toward deep reds and faint infrared, like a photograph left too long in the sun. As the fuel runs out, the cosmic inventory shifts from living stars to leftovers. White dwarfs cool toward blackness as they radiate away their stored heat, sliding down a thermal curve that takes longer than most cosmic eras. Neutron stars spin down as magnetic braking drains their rotational energy, and their once lighthouse beams go quiet. Any remaining heat leaks away, photon by photon, into an expanding sea of background radiation. Planets become frozen rocks, then slowly eroded by rare impacts, cosmic rays, and the steady sputtering of atoms from their surfaces. Even stable matter is not guaranteed to last if protons decay, as some grand unified theories suggest, because then the very idea of solid becomes temporary. The timeline is uncertain, but the direction is not, and the arrow points toward dispersion. There is historical weight behind this arrow. In the 19th century, thermodynamics taught physicists that heat flows from hot to cold and never naturally reverses, and that insight became a cosmic forecast once general relativity and expansion entered the picture. The second law is not merely a rule of engines, it is a statement about probability, about how many microstates correspond to disorder compared with order, and the universe has an overwhelming statistical bias toward the bland. Heat death is that bias written on the largest canvas. Galaxies themselves do not last as coherent cities of stars. Encounters and mergers rearrange them, and gravitational interactions fling many objects into intergalactic space, where they drift as lonely points in a nearly empty dark. Within bound groups, close passes act like slingshots, trading energy until many stars are ejected and only the tightest systems remain. The expansion of the universe isolates bound groups from one another, making each island of matter increasingly alone. In the far future, most of the observable universe becomes unreachable, not because light fails, but because space grows between us and carries distant regions beyond any future signal. The cosmic horizon becomes less a line we could cross, and more a limit on what can ever matter to us. Eventually, the dominant actors are black holes. They are the densest repositories of mass and the deepest sinks of entropy, because their horizons hide information in a way that looks, from outside like irretrievable loss. In a fading cosmos, black holes become the final engines, not because they create order, but because they store energy and release it slowly through subtle processes. They swallow stray matter, merge in rare but titanic collisions, and settle into quiet as gravitational waves ripple outward and then thin into insignificance. For a time, they are the last places where something still happens, and the last places where the universe still has a centre of activity. To picture this era, imagine a black sky with almost no stars, punctuated only by occasional faint glows from accretion. Brief, localised fireworks as a wandering remnant falls into a horizon, then the fireworks stop. What remains are black holes as silent masses, each surrounded by emptiness so vast that even the idea of a neighbourhood loses meaning. The universe becomes a sparse museum of extreme objects, and the exhibits are separated by distances that grow faster than any traveller could cross. Then even black holes are not forever. Hawking radiation predicts that black holes leak energy as quantum fields fluctuate near the horizon, producing particles that escape as if the hole had a temperature. The process is unimaginably slow for large holes, but the mathematics is clear, and the rate depends strongly on mass. A stellar mass black hole would take far longer than today's cosmic age to evaporate, while a supermassive one would endure for timescales that dwarf even that. Over vast spans, black holes evaporate, shedding mass into thin radiation, and their temperatures rise as they shrink. The final flashes are brief and small compared with the age that precedes them, like a match struck after eons of darkness. After the last evaporation, the universe is close to a pure bath of low-energy photons and other nearly massless particles. Any remaining matter is either extremely dilute or absent, depending on the true stability of particles and the fate of any long-lived remnants. Temperature trends toward a limit set by expansion, and density trends towards zero, because volume grows while content thins. This is the classic quiet fade-out. It is the end written by thermodynamics, with no dramatic curtain call, only a long approach to sameness. The universe does not stop so much as it loses the ability to do anything distinguishable. But heat death raises a deeper problem than darkness. Time is not just a number on a page. Time is measured by change, and change is tracked by clocks, and clocks require physical processes that repeat or decay at a definable rate. If everything massive is gone, and only massless particles remain, what counts as a clock? If nothing can form a stable bound system, what defines duration? When we say later in such a world, later than what, and measured by which rhythm? In ordinary physics, mass sets scales. Mass gives atoms their sizes through quantum mechanics, sets decay rates through particle interactions, and anchors rulers and clocks by providing stable bound states. With only radiation, the universe has motion but no preferred rest frame, and no natural yardsticks. Because scale becomes slippery, photons always move at light speed, and they do not carry an internal ticking like a spinning planet or a vibrating atom. In that limit, the question becomes unsettling. Does time still have operational meaning, or is it only a coordinate we keep writing out of habit, like a label on an empty map? This is where the documentary's mystery enters, because the far future is not merely a destination but a stress test. The standard model says the universe asymptotically approaches a featureless state, and that is that, with dynamics fading into near nothing. Yet some physicists ask whether the far future could be reinterpreted, not as a terminal state, but as a boundary that can be mapped into something new. The idea sounds like metaphysics until it becomes geometry, because geometry decides what counts as the same when scales disappear. Under the right lens, an ending might be mathematically indistinguishable from a beginning, not by miracle but by symmetry. One proposal makes that claim with unusual boldness. Conformal cyclic cosmology, or CCC, argues that the universe is not a one-time story. It is a sequence of aeons, each beginning with a Big Bang-like event and ending in an ultra-dilute, radiation-dominated future, where the last structures dissolve. The bridge between aeons is not a bounce of matter. It is a rescaling of space-time itself, a change of the ruler rather than a reversal of the arrow. CCC starts from a specific observation about massless physics. For particles with no mass, only angles and light cones matter, not absolute distances, because there is no rest frame in which a particle can sit and define a scale. The equations become conformally invariant, meaning the geometry can be stretched without changing the essential behaviour of those fields. In an extreme future where everything effectively behaves as massless, CCC says the universe loses its intrinsic scale. If scale disappears, infinity can be reinterpreted, because infinitely large is a statement that depends on having a yardstick. In that picture, the infinite future of one aeon can be conformally squashed into a finite boundary. That boundary can then be identified with the Big Bang of the next aeon, because both are dominated by radiation and lack a meaningful scale. The claim is not that the same matter cycles back, or that galaxies return like seasons. The claim is that the causal structure of spacetime continues, while the notion of size resets and the bookkeeping of distances is replaced. The last light becomes the first light, once geometry is allowed to change its ruler, and once late stops meaning what it used to. The idea depends on a crucial condition. Massive particles must either decay, lose mass, or become irrelevant compared with radiation, because mass would reintroduce a scale and spoil the conformal trick. CCC often leans on the possibility that rest mass might fade in the deep future, or that only massless degrees of freedom matter at the boundary, even if some massive relics technically persist. This is not established physics. It is a hypothesis about what survives when the universe has run out of structure, and about which terms in the equations still count. CCC turns that uncertainty into a doorway, and it invites us to ask whether mass is permanent or emergent. The guide and provocateur behind CCC is Roger Penrose. He is a Nobel laureate celebrated for work on black holes and the deep geometry of spacetime, including theorems that made gravitational collapse mathematically unavoidable under broad conditions. He's also known for resisting fashionable consensus when he thinks the math points elsewhere, even when the alternative is hard to test. Penrose has a reputation for ideas that are elegant, difficult, and sometimes infuriating. His proposal matters even if it is wrong, because it forces cosmology to define what it means by an end and what counts as an explanation. Penrose's contrarian streak is not mere contrariness. CCC is framed as a conservative extension of known principles, especially the behaviour of light and the role of conformal geometry, which has a long pedigree in relativity. It tries to avoid speculative new fields that drive a bounce, and instead uses the universe's own dilution as the mechanism that makes the mapping possible. The model asks us to take the far future seriously, not as an afterthought, but as a boundary condition that shapes the whole story. It also asks us to accept that what looks like infinite time might be a coordinate artifact, an illusion produced by insisting on a ruler that no longer exists. A cyclic model must face a hard requirement. It must leave traces that can be checked, because otherwise it is only philosophy dressed in equations. CCC claims it does. Penrose and collaborators have argued that violent events in the previous aeon, like supermassive black hole mergers, could leave imprints that survive the conformal mapping. Those imprints would appear as subtle patterns in the cosmic microwave background, the oldest light we can observe because the CMB is our earliest photograph of a hot, dense universe. The CMB becomes a potential message from before our beginning, written not in words but in statistics. The proposed signals are often described as low-variance circles or other anomalous structures in the CMB. The claim is that these features could be echoes of energy released before our Big Bang, compressed into our early universe, and then stretched across the sky. The counterclaim is that the CMB is a noisy statistical field, and that apparent patterns can emerge by chance when humans search a complex map for shapes. Different analyses reach different conclusions depending on methods, simulations, and assumptions about foregrounds and noise. The evidence is disputed, and that dispute is part of the story, because it shows how hard it is to separate cosmic meaning from statistical coincidence. So the tension is set. Mainstream cosmology predicts a quiet fade-out, with heat death as the final state and no sequel, because entropy has nowhere left to climb. CCC suggests the fade-out is not the end, because scale evaporates and geometry can identify the far future with a new beginning, without violating local physics. One view treats the universe as a one-way thermodynamic process. The other treats the end as a conformal boundary that can be turned into a page break, where the next chapter begins with the same kind of light. This tension is not only about preference, it is about what we consider physical, and about which questions are meaningful when the usual measuring tools vanish. If time requires clocks, and clocks require mass, then a massless future challenges the meaning of time itself. If scale is not absolute, then infinity may not be a wall, but a misreading of the map. If the CMB contains genuine anomalies, then the early universe might carry scars from a previous aeon, faint fingerprints in ancient radiation. If it does not, CCC may still be a useful provocation that clarifies why the standard story is so compelling and why thermodynamics feels so final. The hook is simple and unsettling. What if the universe's final, cold breath is not an ending but a disguised beginning? What if the last black hole's evaporation is not the last event, but the last event we can describe using our current rulers, clocks, and intuitions? In that case, the end of everything is not a point in time. It is a change in what time can mean, and in what counts as a measurable fact. To follow this mystery, we need two things. We need the standard ending in full detail, because any alternative must match it where it works, and must respect the same thermodynamic constraints. And we need to understand what physics survives when structure is gone, because CCC lives in that limit, where only light cones and angles remain. The next step is to walk through the orthodox timeline of cosmic decay, from fading starlight to evaporating horizons, and ask what remains when the universe runs out of clocks. Heat death is the mainstream endgame because it follows two stubborn facts that refuse to negotiate. The universe expands, and the second law of thermodynamics favours higher entropy states over lower ones. Put together, those facts imply a future where usable differences fade, slowly, relentlessly, until almost nothing can happen. Entropy is not just messiness, and it is not a moral label pinned to disorder. In physics, entropy is a count of microscopic configurations consistent with the same macroscopic appearance. It is the number of hidden ways a system can be arranged while still looking, from afar, like the same thing. That definition matters because macro is what we can measure, while micro is what we usually cannot. A thermometer reads one number, yet the molecules beneath it can be arranged in countless patterns. Entropy is the bridge between those levels, and it turns ignorance into a precise quantity. Imagine a deck of cards laid out in perfect order on a felt table under bright studio lights. There are very few arrangements that look exactly like that tidy sequence, yet there are astronomically many that look scrambled. If you shuffle blindly, you almost always move toward the more numerous outcomes, because probability leans heavily toward the common. Now scale that intuition up to gases, plasmas, and galaxies, and the logic stays the same. A state is not one arrangement, but an entire family of arrangements that share the same visible summary. The summary might be pressure and temperature, or it might be density and expansion rate across cosmic space. That statistical bias becomes the arrow of time in physics, and it does so without any need for intention. The future is the direction in which the number of compatible microstates typically increases. We experience later as the direction where more arrangements are available, and therefore where change is more likely. This is why irreversibility feels so absolute, even though the underlying laws can be time-symmetric. Newton's equations and even quantum dynamics do not demand that a cup must shatter rather than reassemble. The second law emerges because the reassembly would require an absurdly special coordination among countless microscopic degrees of freedom. A useful way to picture this is a landscape of possibilities, with valleys representing common states and narrow ridges representing rare ones. Ordered arrangements sit on those ridges, precarious, unlikely, and easily lost. Once a system tumbles into a broad valley of high multiplicity, it is not forbidden to climb back up, but it is fantastically improbable. In everyday life, entropy rises because systems exchange energy and information with surroundings. A hot mug cools because it shares energy with the room, and the room shares it with the wider building. In cosmology, the surroundings are the rest of the universe, and the rest is unimaginably large. The key idea is free energy, not energy itself, because raw energy can be useless without structure. Complexity needs gradients that can be tapped, like hot versus cold or dense versus sparse. A waterfall matters because of height difference, and a battery matters because of chemical separation. In thermodynamic language, it is the ability to extract work that counts, and that ability is always conditional. Work requires a path from high potential to low potential, and it requires constraints that prevent immediate equalization. Without constraints, energy spreads out too smoothly, and nothing can be steered. When gradients flatten, the ability to do work collapses, even if energy still exists in abundance. Heat death means usable differences become too rare to matter, not that the universe runs out of energy. Energy remains, but it becomes trapped in forms that cannot be organized into engines. Classical thermodynamics was built on boxes, pistons, and steam engines, where the container is fixed and the walls stay put. Cosmology adds a twist that classical thermodynamics did not face. The container is not fixed because spacetime itself grows. The box is the geometry, and the geometry changes. That change is not a metaphor, and it is not a motion through space like debris flying outward. In general relativity, expansion is encoded in the metric, the rule that tells you what distances mean. The scale factor grows, and with it the separation between co-moving points that are simply carried along by the cosmic flow. Expansion matters because it dilutes matter and stretches radiation, and both effects weaken interaction. As volume increases, densities fall, collisions become rarer, and reaction rates slow. Even processes that are possible in principle become irrelevant in practice, because the universe becomes too thin to keep them going. Visually, you can imagine a glowing fog of particles that slowly spreads out across a darkening stage. At first, sparks collide, fuse, and scatter light in every direction. Later, the same fog becomes so rarefied that the sparks almost never meet, and the stage looks empty even though it is not. The cosmic microwave background already shows this cooling trend in a measurable, almost intimate way. Its temperature drops as the scale factor grows, because photon wavelengths are stretched by expansion. A photon's energy is tied to its wavelength, so redshift is not just a color change, it is a draining of usable energy. Today the microwave background is about 2.7 Kelvin, a faint afterglow that fills every direction like a whisper. In the deep future, that glow will slide to longer and longer wavelengths, becoming radio, then something even more diffuse. The universe does not turn off, but it becomes harder to distinguish from silence. If you could watch that background with impossible patience, you would see its spectrum glide downward like a note falling below hearing. Peaks shift, intensities thin, and the sky's last uniform light becomes a stretched, cold haze. It is a visual quieting that mirrors the thermodynamic one. In the far future, the average temperature trends toward near zero, but the approach is subtle and never quite simple. It does not guarantee absolute zero, because horizons and quantum fields complicate the limit. Even empty space in modern field theory is not truly empty. Its lowest energy state still seethes with fluctuations. Those fluctuations are not free energy waiting to be harvested at will, because they do not provide a stable gradient. They are jitter without a handle, and they average out when you try to build a macroscopic machine. Yet they remind us that nothing is a physical medium with rules, not a blank void. Maximum entropy in an expanding space-time is not a single frozen picture, like a gas perfectly mixed in a sealed room. It is an asymptotic approach where no remaining process can create new, large gradients. The universe can keep changing in tiny ways, yet the changes stop producing new structure that matters on macroscopic scales. Gravity seems like the enemy of heat death because it clumps matter into stars and galaxies, creating striking contrast. Yet gravity also has its own entropy story, and it drives structure toward black holes. In a gravitating system, uniform can be low entropy because there are many more ways to be clumpy than perfectly smooth. A smooth gas cloud can lower its ordinary thermal entropy by collapsing, because the gas becomes more ordered locally. The total entropy still rises because gravitational degrees of freedom open vast new possibilities. In plain terms, gravity creates new ways for the universe to be, and those ways overwhelmingly involve concentrated structures. This is why the universe can form galaxies and stars while still obeying the second law. Local order grows by spending gradients and exporting entropy outward. A star shines by turning concentrated nuclear fuel into a flood of low-grade photons, and those photons carry entropy away into surrounding space. You can picture it as a trade. A small region becomes organized, but only by making the outside more disorganized. The star's core is a furnace with a steep gradient, while the interstellar medium is a sink that accepts the waste heat. The arrow of time is written in that outward flow. The standard timeline is a sequence of diminishing energy sources, and it reads like a slow dimming of cosmic options. Each era ends when its dominant gradients are exhausted or locked away. The universe does not choose to end an era, but the bookkeeping of free energy eventually closes the account. First comes the stelliferous era, when stars shine and chemistry has steady power across billions of years. Fusion turns mass into radiation, and starlight maintains temperature differences between illuminated surfaces and cold space. Planets, atmospheres, oceans, and any complex chemistry are parasitic on that steady gradient. In this era, the night sky is crowded, and the universe is visually busy with luminous disks and spiral arms. Gas clouds collapse, ignite, and blow winds back into their galaxies, enriching them with heavier elements. Those elements matter because they make rocky planets, complex molecules, and the intricate chemistry that depends on them. The physics of fusion is itself a story of gradients and barriers, because nuclei must overcome electrostatic repulsion. In stellar cores, pressure and temperature are high enough for quantum tunneling to help reactions proceed. The result is a slow leak of binding energy into space, controlled, long-lived, and astonishingly productive. Star formation slows as cold gas is consumed, heated or expelled by feedback from supernovae and active galactic nuclei. Galaxies age into populations of long-lived red dwarfs and fading remnants. The bright, massive stars die quickly, leaving behind a quieter, redder cosmos dominated by smaller, steadier suns. On timescales of trillions of years, most luminous stars are gone, and the cosmic light budget collapses. The sky becomes a record of leftover objects rather than ongoing creation. What remains are dim red dwarfs, occasional mergers, and the slow cooling of stellar corpses. Imagine the visual palette shifting as well, from brilliant blue-white points to a deep ember-red sparsity. The bright nebulae fade because there are fewer ultraviolet sources to excite them. Even the concept of a galaxy changes, as spiral arms lose their contrast and become ghostly stellar halos. Then comes the degenerate era, dominated by white dwarfs, neutron stars, and brown dwarfs. These are not engines, but embers cooling in slow motion, each one a compact archive of past fusion. Their internal pressure is supported by quantum mechanics, electron degeneracy in white dwarfs, neutron degeneracy in neutron stars. Degeneracy pressure is strange because it is not thermal, and it does not require heat to persist. It arises from the Pauli exclusion principle, which limits how tightly identical fermions can be packed into the same quantum states. In plain terms, matter resists compression because its quantum seating chart runs out of available seats. White dwarfs radiate away stored heat and approach black dwarf states over unimaginable durations. Their glow fades from white to red to infrared, until they are almost indistinguishable from the cold background. Neutron stars spin down and lose magnetic energy, and their once fierce beams become quiet, intermittent, then absent. Brown dwarfs, too small to sustain hydrogen fusion, cool steadily after their brief early warmth. They become dark spheres drifting through expanding space, occasionally perturbed by passing masses. In this era, the universe still contains matter, but matter increasingly lacks the gradients needed to stay interesting. Planetary systems, if they remain bound, become dynamically unstable over immense times, because gravity never truly rests. Encounters and resonances eject bodies into interstellar and intergalactic space. A planet can be thrown outward like a coin flicked from a table, leaving its star behind forever. In dense regions, gravitational interactions act like a long casino game played with orbital energy. Energy is traded until many objects are flung out and only tight binaries survive. The winners are compact pairs, white dwarf binaries, neutron star binaries, because tight systems are harder to disrupt. Even those binaries are not permanent in the deepest sense, because they can radiate energy away. Gravitational waves carry orbital energy into the void, and the orbit shrinks. Over colossal spans, some pairs merge, producing brief flashes of heat and motion, rare punctuation marks in a mostly quiet epoch. The details depend on uncertain physics, including whether protons decay, a question that ties cosmology to particle theory. If proton decay occurs, even degenerate matter dissolves into leptons and radiation. The very atoms that make up white dwarfs would not be eternal, and solidity would be a temporary illusion. If protons are stable, matter can persist longer, but it still becomes isolated and inert as expansion separates everything. Either way, the supply of accessible free energy keeps shrinking. The universe is not running out of stuff, but it is running out of ways to make that stuff do anything coordinated. The next era is shaped by black holes, which become the dominant structured objects in the long run. They are the natural endpoints of collapse and the deepest sinks of entropy. When matter falls past a horizon, the outside universe loses access to its detailed configuration, and that loss has a thermodynamic price. Black hole entropy is not a metaphor. and it is not optional if we take quantum theory seriously. Bekenstein and Hawking showed that a black hole has an entropy proportional to horizon area. That result links gravity, thermodynamics, and quantum physics in a single unsettling equation. The area law is startling because it scales like surface, not volume, and it defies ordinary intuition. It suggests the information capacity of a region is tied to boundaries in space-time. In a sense, that is precise, not poetic. The horizon behaves like a storage surface for microscopic degrees of freedom. If you visualize it, the black hole is less like a bottomless pit and more like a boundary with bookkeeping. The horizon is a one-way membrane for classical signals, yet it also acts like a thermodynamic object with temperature and entropy. The universe, in effect, keeps accounts on surfaces. For cosmology, the practical result is clear and measurable in principle. Supermassive black holes dominate the entropy budget of the observable universe today. Even though they occupy tiny volumes, their horizon areas are enormous, and entropy counts possibilities, not size. That dominance matters because it reframes what maximum entropy means in a universe with gravity. The universe can increase entropy dramatically by making and growing black holes. Collapse is not a rebellion against the second law. It is one of the most efficient ways to satisfy it. As galaxies evolve, black holes merge and accrete, then settle into quiet. The last major entropy production events are likely gravitational and horizon-driven. Visually, the universe's final fireworks are not bright invisible light, but deep in space-time itself, ripples, mergers, and the swallowing of matter. At this point, expansion is not just background scenery behind the drama. It becomes a causal filter that decides which regions can ever interact again. If the expansion accelerates, it does more than spread things out. It draws boundaries around what can influence what. Dark energy appears to drive accelerated expansion in our current data, inferred from supernova surveys and the large-scale structure of galaxies. If it remains constant, the universe approaches a de Sitter-like future. That phrase is technical, but the picture is simple. Exponential stretching that never lets up. Acceleration creates an event horizon, a boundary beyond which signals sent now never reach us. It is not a wall in space, but a limit on causal contact. Light can still travel locally, yet the space between distant regions grows so fast that the light never closes the gap. Over time, galaxy groups become isolated islands, each one gravitationally bound and surrounded by expanding emptiness. Distant galaxies redshift away and cross the horizon, leaving each bound region increasingly alone. The sky, from within any one island, becomes emptier not because galaxies vanish, but because they become unreachable and undetectable. The image is hauntingly simple. A local cluster still has stars, remnants, and a central black hole. Yet beyond it, the cosmos becomes a black curtain. The most distant galaxies do not explode or disappear. They just slide beyond the limit where any message can return. What does universe mean when most of it is causally inaccessible? This isolation raises the stakes for any future to beginning connection we might imagine. If regions cannot communicate, any global reset must be geometric rather than dynamical. You cannot rely on matter mixing across the cosmos if the cosmos has fractured into causally separated domains. In an accelerating universe, even the meaning of temperature of empty space changes in a way that feels almost like a trick. Horizons carry an associated temperature and entropy, like black holes. A de Sitter horizon has a faint thermal character, implying that even nothing comes with a minimal thermodynamic signature. That temperature is extraordinarily small, yet conceptually it is huge, because it ties cosmic expansion to thermodynamic limits. It suggests the future vacuum is not merely cold, but thermally textured by geometry. Even if no atoms remain, spacetime itself still sets a faint statistical background. So maximum entropy is not simply everything mixed in one box at one uniform temperature. It is a balance between matter, radiation, black holes, and horizon structure in expanding spacetime. The end state is not a tidy equilibrium snapshot, but a regime where no new macroscopic contrast can be sustained. Then comes the key reversal of intuition, the turn that makes the story eerie rather than merely quiet. Black holes do not last forever, even though nothing classical escapes them. Their apparent permanence is a classical illusion, and quantum theory refuses to cooperate with that illusion. Hawking radiation arises from quantum fields near the horizon, where the vacuum behaves like an active medium. The vacuum is not empty, and fluctuations can produce escaping particles with a thermal spectrum. The popular story speaks of particle pairs, yet the deeper point is that curved spacetime reshapes what nothing means. From far away, the black hole behaves as if it has a temperature inversely proportional to its mass. Large holes are colder, and they evaporate more slowly. Small holes are hotter, and their evaporation accelerates as they lose mass, like a candle that burns faster as it shrinks. For stellar mass black holes, evaporation times are immense compared with today's age, dwarfing the age of stars. For supermassive black holes, the times can reach around 10-100 years, a number so large it breaks ordinary intuition. Written out, it is a 1 followed by 100 zeros, a timescale beyond any familiar comparison. During most of that time, nothing dramatic happens from an outside perspective, and the universe continues its slow dilution. The black hole very slowly loses mass, and the surrounding universe keeps thinning. The background temperature keeps dropping, and eventually the black hole becomes warmer than its environment, making net evaporation inevitable. As the black hole shrinks, its temperature rises and the evaporation accelerates, shifting the emitted spectrum to higher energies. The final stage is brief compared with the eons that precede it. In that last instant, the black hole's remaining mass converts into a burst of particles, a final flare in a universe that has forgotten brightness. When the last black holes evaporate, the remaining content is mostly low-energy radiation and other nearly massless particles. Structure becomes a memory with no keeper. The last compact archives of complexity dissolve into a thin, nearly uniform bath of quanta moving at light speed. This is the dark era in the classic forecast, and it is dark in more than one sense. It is not a sudden blackout, but an asymptote toward featurelessness. The universe approaches emptiness the way a sound fades in a vast hall, not with a click, but with a long, thinning tail. The universe still has motion and fields, but it lacks engines that can run for long. Without gradients, there is no sustained complexity, no long-lived chemistry, and no stable ecology of change. You may still have particles, but you do not have the persistent differences that let particles build anything durable. Heat death is often misunderstood as a single moment when everything stops, like a machine switched off. In reality, it is a long approach where the rate of meaningful events trends towards zero. Events still occur, but they become so rare and so energetically small that the cosmos loses its narrative texture. Even the word cold becomes slippery in this limit, because temperature is an operational concept. Temperature can be defined for radiation, yet there may be no observers or devices to operationalize it. A thermometer is itself a physical system with internal degrees of freedom, and those degrees of freedom require gradients to function. The deeper issue is not darkness, but scale, and scale is normally anchored by mass. Physics is usually expressed with rulers, clocks, and masses that set reference units. We do not just talk about meters and seconds. We build them from stable processes, from atomic transitions to orbital periods. If the far future is dominated by massless particles, those reference units lose their anchors in a way that is easy to miss. Photons have no rest frame and no internal ticking that defines duration. A photon does not carry a built-in clock, and it does not provide a natural at-rest yardstick. Distance becomes hard to define without bound systems that can hold a rigid separation. Time becomes hard to define without repeatable processes that can serve as clocks. In a universe of free-streaming radiation, everything moves at one speed, and the usual notion of waiting becomes less physical. We can still write coordinates on a manifold, and mathematics will still allow us to label events. But coordinates are not measurements, and labels are not standards. Measurement requires physical standards that survive long enough to compare, and it requires localized systems that can store records. This is the crack in the wall where the central question returns, and it returns with sharper teeth. After heat death, does the universe truly end? Or can the far future connect to a new beginning? If the tools used to define after dissolve, what exactly are we claiming when we say time continues? The standard story assumes time keeps meaningfully flowing forever, even if nothing much happens. It assumes the far future is just more time, stretched thin but still operational. That assumption is usually left implicit, because in ordinary eras clocks exist and the assumption feels harmless. Yet if everything becomes effectively radiation, the laws gain a special symmetry that changes what scale means. massless physics can be insensitive to overall scale, caring more about angles and light cones. In plain language, if nothing has rest mass, the universe can lose the physical meaning of how big, while keeping the meaning of what is connected to what. That symmetry hints at a strange possibility, and it is why the heat-death story does not fully close the book. If scale stops being physical, then an infinitely large old universe might be redescribed without its usual yardsticks. A description without yardsticks can sometimes be mapped to a description of a different epoch, if the geometry allows it. To see why heat-death became the default expectation, we need its historical spine, because this idea was not born in cosmology. 19th century thermodynamics turned irreversibility into a quantitative law, motivated by steam engines and the limits of industrial power. Clausius formalized entropy, and Kelvin popularized the idea of a heat death for the world, long before modern cosmology existed. Those early arguments were not about galaxies, but about coal, work, and the efficiency of machines. Carnot's insights showed that even ideal engines cannot convert heat into work without a temperature difference. Once that lesson was learned on Earth, it was almost inevitable that thinkers would ask whether the cosmos also spends its gradients. When general relativity and cosmic expansion arrived, the second law gained a cosmological stage that made the old worry feel scientific. The universe looked like a system evolving toward equilibrium, not away from it. Early debates about the fate of the cosmos began to sound like engineering, except the engine was spacetime itself. Modern cosmology adds precision through the cosmic inventory, and it does so with data rather than philosophy. We track matter, radiation, dark matter, and dark energy, then extrapolate their dilution and interactions. The equations are simple in outline, yet the consequences stretch across timescales that dwarf the age of stars. The result is not a prophecy of doom, but a conservative extrapolation from what we measure today. If the parameters stay close to what we measure, gradients keep fading and horizons keep isolating. The forecast is not certain in every detail, but its direction is robust because it relies on expansion and statistics. Still, maximum entropy must be stated carefully, because it is easy to smuggle in the wrong picture. It does not mean every point has identical temperature at all times, because expansion keeps redshifting radiation. It means no available process can create new macroscopic order without an external gradient, and in the far future there is no external reservoir left to borrow from. Black holes make this logic feel final because they hoard entropy behind horizons, hiding microstates from the outside. Hawking evaporation then releases that entropy as diffuse quanta, erasing the last compact structures. The end is not an explosion, but a conversion. Dense, structured objects become thin, unstructured radiation. So the dread in heat death is not violence, and it is not catastrophe in the cinematic sense. The dread is the slow loss of contrast, as if the universe forgets how to draw edges. What once looked like a tapestry of galaxies becomes a nearly uniform field, with only faint stretched out remnants of earlier light. And wonder remains because the end is so clean, almost mathematically elegant in its austerity. The same laws that build stars also predict their exhaustion, and the same geometry that expands space also isolates it. The universe is not betrayed by its rules. It is carried to its conclusion by them. If everything ends as radiation, what remains to define distance, time, and scale? The question is not poetic, because physics depends on operational meaning. Without clocks, what is a second? And without bound matter, what is a meter? And without stable masses, what is a kilogram supposed to refer to? This is where Chapter 2 hands the story forward, and it does so by tightening the mystery rather than resolving it. The orthodox endgame is coherent, but it may also remove the very tools used to describe after. If the framework needed to speak about time dissolves, then forever becomes a claim that needs careful translation. The next step is to treat that removal as a clue rather than a dead end, because clues often look like absences. If time and scale depend on mass and clocks, then a massless future may blur endings and beginnings. The universe could approach a regime where the distinction between very large and very small loses physical bite. We return to the opening hook with sharper edges, and with a clearer sense of what is at stake. What if the universe's final cold breath is not an ending, but a disguised beginning? What if the last era does not merely follow the first, but can be related to it by a change in how scale is defined. We do not accept that answer yet, and we do not reject it either, because the mainstream accounting must be finished with discipline. We first finish the mainstream accounting, then ask what geometry allows when the accounting runs out. Only then can the story pivot from thermodynamic fate to the possibility of a deeper scale-free continuity. Heat death sounds like a thermal ending, yet it also threatens measurement itself, because measurement requires repeatable standards, not just surviving equations. In the usual picture, heat death means maximum entropy and minimal free energy, a cosmos where gradients have been erased and usable work has dwindled away. Stars have long burned out, galaxies have thinned, and the sky has dimmed into a near-uniform bath of redshifted radiation. Even the last warm embers of structure fade, until what remains is mostly empty space and a whisper of long-wavelength light. Yet CCC asks a sharper question beneath that familiar imagery. If the far future contains only massless particles, what does it even mean to compare durations, or to say that anything happens after anything else? If the far future contains only massless particles, physics may keep its formal relations while losing its operational anchors, which is where theory meets the stubbornness of experiment. We could still write symbols for meters and seconds, but nothing would remain to realize them in matter, not even in principle. A theory can be mathematically intact and still be physically mute if no system exists to instantiate its units. The unsettling thought is that the universe might still obey laws, while no longer containing anything that can act as a laboratory. In our current universe, most things we call real are anchored by mass, and that anchoring is more literal than it sounds. Mass allows rest, and rest allows stable systems that can store memory, whether that memory is a bit in a computer, a spin orientation in a crystal, or a chemical bond in a molecule. Even our most refined standards, like atomic clocks, rely on massive constituents held in stable configurations. When we picture a clock, we picture a device that resists being washed away by its surroundings, and that resistance is usually a story about mass and binding energy. Mass is also what lets a system have a rest frame that is not merely a coordinate choice, but a physical possibility for an object you can carry. A massive particle can be at rest in some frame, and that frame defines a local clock because the particle can carry a device that ticks along its own history. A massless particle cannot be at rest, because it always moves at sea, and there is no inertial frame in which it sits still. In the late universe imagined by CCC, the very notion of sitting still becomes harder to cash out. This difference is not philosophical, it is built into relativity's geometry, into the sign of the interval and the structure of space-time itself. Massive objects trace time-like paths, and massless quanta trace null paths, and those two kinds of paths sit on different sides of the same causal boundary. In a Minkowski diagram, time-like world lines live inside the light cone, while null world lines ride the cone's surface like a razor-thin edge. Visually, it is the difference between a path with thickness and a path that clings to the limit of what causality allows. Along a time-like path, proper time accumulates, and a wristwatch can in principle tick, recording a sequence of internal states. Proper time is not a convention. It is the invariant length of a world line measured by the spacetime metric. Two observers can disagree about coordinate time, yet if they reunite, they agree on the proper time each has experienced. This is the famous twin paradox lesson, made precise by geometry rather than by storytelling. Along a null path, proper time is zero, in the strict relativistic sense, and that is a mathematical statement with operational consequences. The interval along a light ray is neither positive nor negative, and the metric assigns it no elapsed proper time at all. This is why the phrase "photons don't experience time" persists, even though it must be handled with care. The phrase is shorthand for a geometric fact, not a claim about what light feels. So we say, carefully, that for light there is no experienced passage of time, meaning no proper time along a null trajectory, not a claim about awareness. That is not a statement about consciousness. It is a statement about space-time intervals and what the geometry permits. It is also not a denial that light can be emitted, travel and be absorbed. It is a claim about the invariant time measured along that path. In a universe made only of such paths, the usual bookkeeping of before and after loses a familiar reference. Photons still have frequency, and fields still oscillate, and interactions still occur, even in a universe stripped to radiation and thin, rare encounters. A wave can have a period, and a quantum can carry an energy proportional to that frequency. Yet frequency is not a clock unless something can count cycles, store the count, and compare it to another count later. Without memory, repetition is not measurement, it is merely motion. A clock is a physical system that repeats, and that repetition must be stable across disturbances and across time, or else it cannot serve as a standard. Stability usually means a bound system with a characteristic energy scale. Because bound systems resist being smeared out by noise, a pendulum is stable because gravity and inertia define a restoring force, while an atom is stable because quantum mechanics quantizes its allowed states. The deeper point is that clocks are not abstract numbers, they are engineered islands of regularity. Atoms provide clocks because their transitions have fixed energies set by masses and charges, which is why spectroscopy became a backbone of modern physics. The electron mass and the fine structure constant set the scale of atomic spectra, and those spectral lines can be used as exquisitely repeatable references. When we define the second using the hyperfine transition of cesium, we are quietly relying on a hierarchy of masses and couplings that make that transition sharp. Historically, this shift, from Earth's rotation to atomic transitions, was a recognition that the cosmos is messy, while quantum structure is remarkably consistent. Molecules provide clocks because their vibrations depend on reduced masses and bonds, and those masses enter like weights on a spring. The frequencies of vibrational and rotational modes shift if masses change, because the inertia of the nuclei enters directly into the quantum energy levels. Even the chemistry of life, which feels so distant from cosmology, is a tapestry woven from mass scales. If those scales were absent, even the idea of a molecule would dissolve into unbound fields. Even a spinning planet is a clock because its inertia resists change, and because angular momentum provides a kind of persistence across eons of disturbance. Earth's rotation is not perfectly stable, yet it is stable enough that it once defined the day and anchored human timekeeping. Even a decaying particle is a clock because its lifetime is set by couplings and mass scales, and because exponential decay provides a statistical arrow of time. In every case, the universe gives you a repeatable process only because something is heavy enough, or bound enough, to keep repeating. Remove mass, and you remove the natural numbers that define size and duration, at least in the practical sense that physics can operationalize. You can still label events, yet you lose an intrinsic ruler for comparing them, because no bound systems remain to set a preferred scale. Without a scale, twice as long becomes a sentence without a referent. The mathematics still speaks, but the universe no longer supplies the objects that make its words testable. This is the vanishing of scale that CCC treats as a physical clue, rather than a mere mathematical trick. If nothing has rest mass, the universe may still have structure, but not absolute size because only ratios that do not require a fixed unit remain meaningful. The world becomes describable by shapes and causal relations, not by calibrated lengths. It is like keeping the outline of a drawing while throwing away the ruler that set its dimensions. Scale matters because it turns equations into predictions with units, and units are how theory meets observation. A mass implies a Compton wavelength, and that wavelength defines a characteristic length through quantum mechanics, even if we never measure it directly. The Compton wavelength is the scale at which localizing a particle costs enough energy to create new particles, so it marks a boundary between classical intuition and quantum field behavior. In a sense, it tells you when a particle stops behaving like a tiny billiard ball and starts behaving like a field that can spawn copies. A mass also implies a rest energy, and that energy sets characteristic times through quantum relations tying duration to frequency. The relation between energy and frequency, which we write as E equals h bar omega, turns a mass scale into a natural oscillation scale. In practice, masses seed the hierarchy of clocks we actually use, from nuclear transitions to atomic transitions to mechanical resonators. Remove those seeds, and the hierarchy collapses into a scale-free description that cannot be pinned down internally. In the deep future, CCC imagines those hierarchies dissolving, not with a bang, but with a slow loss of reference. The universe becomes dominated by radiation, and the remaining degrees of freedom behave as if massless, because any residual masses become negligible compared to the enormous stretching of wavelengths. The cosmos does not need to be literally empty, it needs to be empty of stable, massive standards. The imagery is stark. a black sky, no stars, and a faint uniform glow whose wavelength keeps lengthening beyond any conceivable detector. That claim is strongest if all massive particles decay, or if their masses effectively fade away as meaningful parameters. It is weaker if stable massive relics remain and keep a scale alive, because even a sparse population of massive particles could, in principle, carry clocks. The argument is therefore not only cosmological, but also particle physical, and it leans on what survives for unimaginably long times. CCC's future is built not only from galaxies and expansion, but from the deep question of what the standard model permits at extreme ages. Penrose argues that the relevant limit is what survives as the universe becomes empty and cold, when the last long-lived structures have either decayed or evaporated. In that limit, only the causal structure might remain physically meaningful, because causal structure does not require a ruler, only light cones. If the universe cannot define a meter, it may still define what can influence what. That is a minimal kind of reality, but it is not nothing. To make that idea precise, we need a minimal language for spacetime geometry. General relativity is not a force law added to space. It is the rule for measuring intervals, an instruction manual for how clocks and rulers behave in the presence of energy and momentum. Historically, this was Einstein's radical move in 1915. Gravity is geometry, and free fall is not a push but a path. The triumph was that the same framework explained Mercury's orbit, the bending of starlight, and later the expansion of the universe itself. The metric is that rule, a field that assigns a distance between nearby events, and it is the central object that turns coordinates into physics. It is written as a tensor, but its meaning can be stated plainly. It tells you how to compute the space-time interval from coordinate differences. From the metric we compute the space-time interval, and the interval tells us what can influence what, because it sorts separations into time-like, null, and space-like. In the documentary's visuals, this is where abstract symbols become geometry you can almost see. Time-like intervals allow slower-than-light travel and proper time for massive observers, which is why they correspond to possible histories of material objects. Null intervals define light rays, and they draw the light cones that bound causality, making a sharp distinction between what can be reached and what cannot. Space-like intervals separate events that cannot be connected without exceeding c, so they cannot be linked by any signal consistent with relativity. These categories are not labels we choose, they are the metric's classification of the world. The light cone is the border, and the metric decides where that border lies, event by event. Change the metric and you change the tilt and shape of light cones, which is why gravity can be described as the bending of causal structure. In a strong gravitational field, the future light cone can tip toward a black hole, making escape increasingly difficult. The picture is vivid. The cone leans, the allowed future narrows, and the geometry itself becomes a kind of trap. In ordinary cosmology, we treat the metric as giving both shape and scale, and we usually keep both without questioning the distinction. The scale factor grows, rulers stretch, wavelengths redshift, and clocks dilate in gravitational fields, so timekeeping becomes a story about geometry as much as machinery. The expanding universe is not objects moving through space like shrapnel. It is the metric itself changing so that distances between moving points increase. The same geometry that defines time also defines the way light thins and cools as it travels. CCC asks what happens when scale stops being part of the physical content, and it treats that loss as an actual physical regime rather than a mathematical curiosity. It focuses on a restricted geometry that keeps light cones fixed while allowing overall rescaling, because light cones encode causality, and causality may be all that survives. This is a subtle shift in what we treat as real in the description. It is also a shift in what we think can be measured when the measuring tools have disappeared. That restricted geometry is conformal geometry. A conformal transformation multiplies the metric by a smooth positive factor, changing lengths but preserving angles, and in spacetime the crucial angles are the null directions. The transformation can stretch or shrink every ruler, yet it cannot change which directions are light-like. In other words, it can change the scale of the drawing while keeping the causal arrows pointing the same way. Preserving angles means preserving the light cones, and therefore preserving causal structure, even while distances and durations are rescaled away. If two events can be connected by light before rescaling, they can after rescaling. because null paths remain null. Conformal geometry therefore keeps the skeleton of spacetime, the network of possible influences, while discarding the flesh of absolute scale. It is a geometry that remembers who can talk to whom, but forgets how far apart they were. Many massless field equations in key limits are conformally invariant or close to it, which is why this symmetry is more than aesthetic. Maxwell's equations for electromagnetism have a special relationship to conformal symmetry in 4 dimensions, and massless wave equations often respect the same structure. Their behavior depends on the light cone structure more than on absolute scale, which is why conformal diagrams can capture their essential propagation. This is also why light, in a deep sense, is the messenger that survives the loss of rulers. This is why Penrose treats massless physics as the natural language of the far future, where only radiation-like behavior remains operational. If only massless quanta remain, the universe may become effectively conformal, because the remaining dynamics do not care about overall rescaling. The claim is not that nothing happens, but that what happens can be described without a preferred unit. The lingering question is whether description without scale is still a full physical world, or a world stripped down to relations alone. The move sounds abstract, yet it has a concrete payoff for cosmology, because it changes what infinite time looks like on the page. If scale has no intrinsic meaning, then an infinite future can be compressed without changing causal relations, much as a map can distort distances while preserving directions. In a Penrose diagram, infinity can be drawn as a boundary you can point to, rather than a place you can never reach. The visual is a clean, elegant trick, but CCC insists it is more than a trick when clocks no longer exist. Penrose's picture starts with an expanding eon that asymptotically thins toward emptiness, with structure gradually erased by expansion and decay. As time goes on, matter becomes irrelevant, and radiation dominates what is left. Not because radiation gains energy, but because everything else becomes diluted or disappears. The cosmic microwave background, already cold today, would be redshifted to wavelengths larger than galaxies, then larger than clusters, then larger than the observable region itself. In the mind's eye, the last photons become so stretched that their oscillations are slower than any remaining process that could count them. In that asymptotic regime, the metric can be rescaled so the infinite future becomes a finite conformal boundary, a mathematical edge with physical intent. Infinity becomes an edge in a conformal diagram, drawn as a smooth surface rather than a distant horizon. Visually, it is like taking an endlessly stretching sheet and replotting it so its far end fits on the page. The sheet is still the sheet, but the scale markings have been erased. That edge is not a wall of matter, it is a surface where the old scale has been removed, leaving only the causal pattern behind. CCC then proposes matching that boundary to a new beginning, as if the universe's remote future and another universe's earliest moments are 2 descriptions of the same conformal geometry. The end is not a singular crash, it is a limit where our usual yardsticks dissolve. The transition is less like a collision, and more like a change in what counts as a meaningful comparison. The next aeon begins with a big bang that is also dominated by radiation and lacks intrinsic scale, at least in the earliest, most relativistic regime. In standard cosmology, the early universe is hot, dense, and filled with relativistic particles, so masses are often negligible compared to thermal energies. CCC leans on that similarity, suggesting that the beginning already resembles a massless world. In the visuals, the newborn cosmos is a bright, opaque plasma, where light and matter are locked together in a seething, almost uniform glow. The end and the beginning can be identified after conformal rescaling, which is the model's signature move. The match is not a time machine and not a recycling of material content. It is a geometric identification of boundaries. CCC's central claim is that what we call the far future can be re-expressed as a smooth starting surface for a new expansion. It is a proposal about geometry's continuity when scale has become physically meaningless. This is CCC's central claim about the universe after heat death, and it is meant to be read as a statement about what time requires. The far future is not followed by time in the usual sense. It is reshaped into a new start, because usual sense depends on clocks that no longer exist. The proposal is eerie precisely because it turns a physical absence into a mathematical permission. It asks whether the universe can keep causality while letting duration evaporate. The model is careful about what it does and does not assert. Because the temptation to imagine literal cycles is strong, it does not recycle galaxies or preserve detailed structures across aeons, and it does not claim that the Milky Way returns in another cycle. Instead, it preserves causal structure and allows certain energetic events to leave faint transformed traces, because causal influence can, in principle, be carried by radiation. The continuity is subtle, like a watermark that survives when the paper is reprinted at a different scale. The continuity is geometric, not material, and that distinction is the heart of the narrative. If anything crosses from one eon to the next, it is not a chunk of matter but a pattern in the conformal structure, like a ripple that survives when the scale is erased. That is why CCCC discussions often focus on extremely energetic, extremely rare events, where the imprint might be robust under rescaling. The question becomes, what kinds of cosmic signatures are scale-free enough to persist? Yet a conformal matching raises an immediate question about thermodynamics, and it is the question that refuses to be charmed away. If the previous aeon ends at high entropy, why does the next begin in a low entropy state, with the extraordinary smoothness we infer from the cosmic microwave background? This is the biggest conceptual hurdle, because the second law is not optional, and any cyclic story must face it without hand-waving. If entropy is the price of time's arrow, how can the arrow be reset? The early universe was hot, but it was also remarkably uniform, and that combination is the puzzle's sharp edge. Temperature variations in the CMB are only at the level of tens of microkelvin on a 2.7 Kelvin background, which is a startling degree of smoothness for something that should have been chaotic. So why did the universe begin in such an ordered gravitational configuration, rather than in a lumpy state already filled with collapsed structures? The sky, when mapped in microwaves, looks like a near-perfect sphere with only tiny freckles of variation. Penrose's answer separates ordinary thermal entropy from gravitational entropy, and he argues that we have been mixing them too casually. In his view, the early universe was thermally hot but gravitationally ordered, and those are not contradictory statements. A gas can have high thermal entropy while the gravitational field remains smooth, because gravity's disorder is not about particle velocities, but about curvature patterns and clumping. Put simply, heat can be randomized while spacetime remains unusually unwrinkled. A smooth early cosmos has low gravitational entropy because gravity has not yet formed clumps and horizons, which are the gravitational equivalents of messy configurations. The specialness is not low temperature, it is low Weyl curvature, meaning the part of curvature associated with tidal distortions and the free gravitational field. In a universe filled with matter, gravity tends to amplify inhomogeneities, so smoothness is not the generic outcome. The fact that the early universe was smooth is therefore, in this view, a boundary condition of astonishing specificity. Weyl curvature measures the part of spacetime curvature tied to tidal distortion and gravitational radiation, and it is what remains when you subtract the curvature directly sourced by local matter density. It is what makes nearby geodesics shear and stretch, and it is what carries information about gravitational waves in vacuum. Penrose links growing Weyl curvature to the growth of gravitational entropy, because as structure forms, the gravitational field gains complexity in a way that resembles increasing disorder. The cosmos begins with a quiet gravitational field, then gradually learns to roar. Black holes then become the main carriers of gravitational entropy, because horizons hide enormous numbers of microstates behind a one-way boundary. The Baconstein, Hawking entropy, scales with horizon area, not volume, which is already a clue that gravity counts states differently. A single supermassive black hole can dominate the entropy budget of an entire galaxy, dwarfing the entropy of all its stars and gas. In the far future, those horizons are like vaults of disorder, storing the universe's gravitational bookkeeping. The late universe is high entropy largely because of gravity, not merely because particles are randomized in a thin gas. It is not merely that particles are randomized, it is that matter has collapsed into deep wells, and horizons have formed that sequester information from the outside. In that view, the arrow of time is written into the growth of cosmic structure as much as into the mixing of gases. The universe's history is a story of smoothness giving way to clumping, and clumping giving way to horizons. CC proposes that at the conformal boundary, when black holes have evaporated, the relevant gravitational degrees of freedom effectively vanish from the description that matters. Hawking radiation slowly bleeds mass and angular momentum away, and over fantastically long times, black holes disappear into a thin bath of photons and other light particles. What remains is radiation with no scale, and without horizons, the dominant repository of gravitational entropy is gone. The visuals here are haunting. A black hole's silhouette softens, then dissolves into a faint uniform glow. If the Weyl curvature is forced to zero, or becomes irrelevant at the boundary, the next aeon can begin smooth again, at least in the conformal sense CCC requires. The low entropy condition is then geometric, not miraculous, because it is tied to a boundary behavior of the gravitational field rather than to an improbable arrangement of matter. In Penrose's language, the universe begins with a constraint on the free gravitational field. The beginning is special not because matter is arranged just so, but because space-time itself is constrained to be unusually simple. This is a bold claim, and it is not universally accepted, which is part of what makes CCC feel like a live scientific mystery rather than a closed story. Many physicists question whether gravitational entropy can be reset without violating the second law, especially if one insists on a single global accounting across aeons. Others question whether the Weyl curvature hypothesis is a physical law or a boundary condition chosen to make the cycle work. The disagreement is not merely technical, it is about what counts as an explanation. The debate is partly about definitions and partly about dynamics, because gravity's microstates are still obscure. What exactly counts as gravitational microstates, and how do we count them in a quantum theory of gravity we do not yet possess? If we cannot define gravitational entropy precisely, then claims about its erasure or continuity remain suggestive rather than decisive. CCC in this sense sits at the edge of what we can currently formalize. The controversy deepens around mass itself, because mass is the very thing CCC wants to see fade from relevance. CCC often assumes that rest mass fades away in the far future, or becomes irrelevant compared with radiation, because any surviving mass would reintroduce a scale. Penrose's conformal matching works most cleanly when the late universe becomes effectively scale-free. The model therefore leans on a physical expectation that is plausible in outline but uncertain in detail. One motivation is that in an expanding, cooling universe, interactions weaken and massive particles may decay, leaving fewer and fewer stable anchors. Protons might not be eternal, depending on grand unified physics, and even electrons could be destabilized in speculative scenarios, though no evidence requires it today. Another motivation is that without mass, the conformal symmetry becomes exact, so the mathematical identification becomes physically natural. The tension is obvious. The cleaner the symmetry, the more the physics must cooperate, but we do not yet know that all masses can disappear, or that stable massive particles cannot survive forever, quietly keeping a ruler alive. Neutrinos have mass, and their tiny masses still define a scale, even if it is subtle. Dark matter might be massive and stable, and if it is, it could remain as a sparse but persistent population that never becomes truly irrelevant. Even a few enduring masses could, in principle, keep the concept of proper time operational for some observers. If any massive component persists, it can reintroduce a scale and complicate the conformal matching, because a scale-free boundary would no longer be exact. CCC must argue that such remnants do not matter at the boundary, either because they become so dilute that no bound systems survive, or because their influence can be absorbed into the conformal factor without physical consequence. The question is not only whether mass exists, but whether it can still function as a clockmaker. A lone particle is not a civilization, but it could still be a standard in principle. Some versions appeal to speculative physics where mass is not fundamental, or where coupling constants run so that masses effectively vanish in the far infrared. In the standard model, masses arise through the Higgs mechanism, which ties them to a field with a vacuum expectation value, so one can at least imagine scenarios where that effective scale changes. Critics see this as convenience rather than consequence, and they ask for a concrete dynamical pathway rather than a hoped-for symmetry. The model's elegance becomes, for skeptics, a warning sign. Still, CCC's appeal is that it uses known geometric tools rather than a new bounce mechanism, and it tries to make the transition conceptually minimal. It replaces a violent reset with a change of units that becomes physical when units lose meaning, and it tries to make the transition a statement about what can be operationally defined. The mystery is that the far future might be simpler than we assume, not because it is empty, but because it cannot carry standards. What remains is a universe that can still carry causal influence, but cannot carry calibrated time. If only light remains, then the universe may lose the ability to distinguish large from small, and that loss is not just aesthetic. A wavelength can be stretched without limit, but if no mass sets a comparison scale, the stretching is not something any internal observer can calibrate. The cosmos becomes a place where only conformal relationships survive, like a drawing that preserves angles but not distances. The documentary's camera lingers on expanding grids that keep their shape, while their scale markings fade to nothing. In that case, the phrase "after the universe ends" becomes ambiguous, and CCC takes that ambiguity seriously. After requires a clock, and a clock requires a stable scale, and scale requires something like mass or binding energy to make repetition meaningful. CCC turns that ambiguity into a proposal, treating the end of time as a regime where time cannot be operationally defined. The question becomes almost linguistic, but it is anchored in physics. What does later mean when nothing can count? The end of time is not a moment, it is a limit, approached as the universe empties and the last standards decay. It is a condition where the concept of duration loses its physical handle, even if the mathematics still contains a parameter called t. This is not a proof that the universe cycles, it is a reframing of what an ending means, and it asks whether our usual timeline is a coordinate choice that fails at the boundary. If time is what clocks measure, what is time when clocks are impossible? Penrose's conformal diagrams make the idea legible, and they give the narrative a visual spine. They show an eon as a region with light cones intact, and a boundary where scale is removed, so that the infinite future is drawn as a finite line. The next eon attaches at that boundary, inheriting causal structure but not inherited rulers, and the last light of one era becomes the first light of the next. The diagram looks calm, almost simple, which is part of its strange power. Even if CCC is wrong, it forces a hard audit of our assumptions, and that audit is valuable in its own right. We assume time continues because we can write T in equations, yet physics demands operational meaning, and operational meaning demands physical systems that can function as clocks. We assume entropy blocks any sequel, yet gravity's entropy is not the same as a gas in a box, and it may obey deeper bookkeeping than we currently understand. We assume the future is merely more of the same, yet CCC suggests the future might be a change in what can be defined. We assume mass is permanent, yet we do not know its ultimate fate, and we do not know whether the universe has hidden decay channels. Is mass an eternal property, or is it an emergent feature of a particular cosmic phase, tied to symmetry breaking and to the existence of bound states? If the universe can evolve into a phase where mass becomes irrelevant, then our intuition about permanence may be parochial. The thought is unsettling. Perhaps what we call substance is a temporary convenience of cosmic history. So the chapter's question is not whether light can travel forever, because travel is not the same as timekeeping. The question is whether a universe of only light can still define forever, or whether forever is a word that silently assumes a clock. The central question returns with sharper edges. After heat death, does the universe truly end, or can geometry connect the far future to a new Big Bang? And if geometry can do that, what does it mean for the arrow of time we live inside? To test CCC, we must compare it to the standard account of the beginning, because any alternative must match what our best data already demands. That means revisiting the Big Bang, and the problem inflation was designed to solve, because inflation is our best known tool for explaining early smoothness and causal contact. If CCC can replace inflation, it must reproduce inflation's successes without its mechanism. If it can coexist with inflation, it must explain what each is doing that the other cannot. So we turn from the end that races clocks to the beginning that demanded them, and we return to the early universe where scale was set and where the first smoothness must be explained. We turn from the end of timekeeping to the first moments that made time measurable, and the central question returns in reverse. If the far future can become conformally simple, almost indifferent to scale, why was the beginning so sharply distinguished? In cosmology, that distinction is not poetic language, it is encoded in curvature, temperature, and the way horizons carve the sky. On screen, the familiar image of a fireball tries to intrude, but it misleads more than it teaches. The Big Bang is not an explosion into pre-existing emptiness, with debris flying outward from a center. It is the expansion of space itself, with distances between co-moving points increasing everywhere at once. In that framework, there is no central blast site, no privileged direction, and no outer edge to crash into. A better visual is a grid drawn across darkness, each square stretching as if the paper itself were being pulled. Galaxies are not shrapnel moving through space, they are markers embedded in space as it grows. The recession we measure is largely geometric, encoded in the metric that general relativity assigns to the universe. When we say the universe expands, we mean the scale factor changes, and with it the meaning of distance. Even the redshift is not a Doppler trick alone. It is the stretching of wavelengths as spacetime stretches. This idea has a history that is quieter than the popular myth, and it unfolded through argument as much as observation. In the 1920s, Georges Lemaitre combined Einstein's equations with astronomical redshifts and proposed an expanding cosmos. Einstein had first introduced a cosmological constant to hold the universe static, then reportedly called it a blunder when expansion became plausible. Edwin Hubble's observations then revealed a linear relationship between distance and recession speed, and the implication was hard to ignore. The universe had not always looked the way it looks now, and the past was denser. The Big Bang model, in its modern sense, is a description of an early hot, dense state and its subsequent cooling. It is a framework for how the universe evolves once it is already expanding and filled with matter and radiation. It is not, by itself, a complete story of the absolute beginning, and it does not automatically explain why the initial conditions had their particular values. Even the word beginning becomes subtle when the equations are pushed toward extreme densities. At those extremes, quantum effects are expected to matter, yet we do not have a finished quantum theory of gravity. As we rewind, the universe does not simply get smaller, it gets hotter, because radiation is blue-shifted as the scale factor shrinks. Photons gain energy, particle collisions become more frequent, and the cosmic soup approaches thermal equilibrium. In that early epoch, temperature is not a metaphor but a measurable distribution of energies. The past becomes a laboratory where particle physics and gravity share the same stage. The same equations that govern accelerators and reactors begin to govern the sky. The evidence for a hot early universe is broad and mutually reinforcing, and it arrives from very different directions. Light element abundances match predictions from primordial nucleosynthesis in the first minutes. The cosmic microwave background is the cooled afterglow of that early plasma, still washing over us from every direction. The expansion history also ties together galaxy redshifts, cosmic ages, and the growth of structure under gravity. These are separate lines of evidence that converge on the same early conditions. Nucleosynthesis works because the early universe was hot enough for nuclear reactions, yet not so hot that nuclei could survive for long. In the first second, protons and neutrons interconverted through weak interactions, and their ratio tracked the temperature. As the universe cooled below roughly a mega electron volt, those weak reactions froze out, leaving a neutron fraction that would soon be locked into helium. Neutrons also decay, so the clock between freeze-out and fusion quietly matters. A few minutes later, when deuterium could finally survive without being immediately photodissociated, nuclear fusion proceeded rapidly. The deuterium bottleneck is a simple phrase for a precise balance between photon energies and binding energy. Once that bottleneck breaks, helium-4 forms efficiently because it is tightly bound and energetically favoured. On screen, the plasma can be shown as a seething bath of particles, where brief nuclei flicker into existence and vanish until the temperature drops enough. The timing matters, and the timing is set by expansion. Reaction rates depend on density and temperature, while the Hubble rate sets how quickly conditions change. As expansion cooled the plasma, reaction rates fell and abundances froze in, like a chemical process quenched midstream. Hydrogen and helium emerged as the dominant products, with traces of deuterium and lithium left behind as sensitive thermometers of the early density. These are not arbitrary numbers, they are fossils that constrain the baryon content of the universe. When astronomers measure primordial deuterium in pristine gas clouds, they are effectively reading a relic of the first few minutes. When they infer helium fractions in old stellar populations, they are checking the same early recipe. The remarkable point is not that the predictions are perfect, but that a simple expanding, cooling model lands close to what the sky reports. That agreement turns the early universe into something like a controlled experiment, performed once and observed forever. It also means that any alternative origin story inherits strict numerical obligations. The CMB works because the early universe was once opaque to radiation, more like the interior of a star than empty space. Electrons and nuclei scattered photons constantly through Thomson scattering, keeping matter and light tightly coupled. In that regime, photons could not travel far without colliding, so the universe had no long-range transparency. The cosmos glowed, but the glow was trapped. It was a bright fog, where light existed everywhere and yet could not go anywhere. As expansion continued, temperature dropped to a few thousand Kelvin, and a crucial transition occurred. Electrons combined with nuclei to form neutral atoms in a process called recombination, although it was really the first durable combination. With fewer free electrons available, the scattering rate collapsed, and photons decoupled from matter. The universe became transparent, and light began to free stream across cosmic distances. The surface we see is not a wall. It is a last scattering shell defined by probability. That released light still fills the sky today as a nearly perfect blackbody spectrum, a curve so clean it looks engineered. Its present temperature is about 2.7 Kelvin, and its spectrum matches thermal equilibrium to astonishing precision. This is one of the most persuasive signatures of a hot origin, because it is hard to counterfeit. The CMB is not just radiation, it is thermal radiation, cooled by expansion. On screen, the spectrum can appear as a smooth arc overlaid with data points that cling to it almost unnervingly well. Yet the CMB is not perfectly uniform, and the imperfections are where the story becomes intricate. Tiny anisotropies appear at the level of tens of microkelvin, mapped as mottled patterns across the celestial sphere. On screen, the smooth orange glow resolves into speckles and swirls, like weather patterns on a planet that spans the universe. Those anisotropies encode the seeds of later structure, and they do so with a statistical regularity that can be measured. Each spot is a record of density, velocity, and gravitational potential at last scattering. The standard expansion history also fits the observed Hubble flow and the large-scale distribution of galaxies, which form a web of filaments and voids. It ties together redshift, cosmic ages, and the growth of structure under gravity, using a small set of parameters. In this picture, the universe is about 13.8 billion years old, and the CMB comes from when it was roughly 380,000 years old. The same model that predicts the CMB also predicts how density fluctuations evolve. The web we map in galaxy surveys is the late-time echo of those early ripples, yet the same model raises sharp puzzles when pushed back toward the earliest times, and these puzzles are not cosmetic. They are questions about what the equations imply when extrapolated and about what must be assumed. The closer we approach the earliest moments, the more the universe seems to demand special preparation. It is as if the initial state was not merely hot, but carefully arranged. The first puzzle is the horizon problem, and it is a problem about causal contact and information flow. Regions of the CMB separated by large angles were never in communication in the simplest Big Bang expansion. Yet they share nearly the same temperature to extraordinary precision as if they had agreed on a common value. The sky looks coordinated across distances that light, in the standard timeline, could not have bridged. Coordination without contact is the kind of clue physicists learn to distrust. To picture this, imagine the early universe as a growing sphere of plasma, with sound waves rippling through it. There is a maximum distance over which any influence can travel, because signals cannot exceed the speed of light. That maximum distance defines a horizon, a causal boundary set by the age of the universe. At recombination, the horizon size corresponds to only a small patch on today's sky. Beyond that patch, the simplest story offers no time for thermal negotiation. In the standard picture without new physics, the early universe expands too quickly for distant patches to equilibrate. Light could not travel far enough before recombination to smooth conditions across the whole sky. The uniformity then looks like coordination without a mechanism, a coincidence written across the microwave background. The question is not whether the universe is uniform, but how it became so uniform. If nature prefers explanations, what did the smoothing? The second puzzle is the flatness problem, and it is a problem about stability and sensitivity to initial conditions. Spatial curvature evolves in a way that makes near flatness fragile under ordinary decelerating expansion. If the universe is close to flat today, it had to be tuned even closer earlier. The numbers become uncomfortable when the clock is wound back. A tiny deviation early can balloon into a dramatic curvature later, unless something suppresses it. In the Friedman equations, curvature competes with matter and radiation as the universe evolves. Matter density falls as the inverse cube of the scale factor, radiation as the inverse fourth, while curvature falls more slowly. In a decelerating universe, that means curvature tends to become more important over time, unless it is extraordinarily small. The early universe then seems to require an implausibly precise initial balance. The discomfort is not philosophical, it is mathematical sensitivity. A visual helps here, a ball balanced on a hilltop, where any tiny nudge sends it rolling away. Flatness is not exactly that, but the analogy captures the instability. The closer the universe is to flat today, the more delicately it must have been set near flatness at early times. We're forced to ask whether this is a brute fact or a clue. If it is a clue, it points toward a dynamical attractor that flattens. These puzzles do not prove the Big Bang is wrong, and they do not erase its successes. They show that the simplest version is incomplete as an origin story, because it leaves key features unexplained. They motivate a mechanism that sets initial conditions into the narrow corridor our observations demand. The theory needs a prelude. The prelude must be brief, powerful, and testable. Inflation enters as that mechanism, and it changes the early timeline without discarding the hot Big Bang that follows. It proposes a brief epoch of accelerated expansion before the hot Big Bang phase, when the universe's energy budget behaved like a temporary vacuum. During inflation, the scale factor grows nearly exponentially for a tiny fraction of a second. In that blink, the universe can expand by an enormous factor. The phrase fraction of a second hides a staggering multiplication of size. Accelerated expansion has a distinctive signature in general relativity. Ordinary matter and radiation slow expansion because their pressure and energy density gravitate. A vacuum-like component with sufficiently negative pressure does the opposite, making expansion accelerate. In equations, it is the combination of density and pressure that matters, and inflation exploits that subtlety. In plain terms, the universe can be pushed apart by a form of energy, whose pressure is effectively tension. On screen, the inflating universe is not a fireball, but a rapidly stretching fabric, where a tiny patch swells to cosmic proportions. Accelerated expansion can enlarge a small, causally connected region into the entire observable universe. It can make distant regions share a common thermal history before they were stretched apart. The horizon problem becomes a memory of an earlier, smaller domain that once fit inside a single causal neighborhood. What looks like coordination is reinterpreted as shared ancestry. Inflation also drives the universe towards spatial flatness in the observable region, and it does so with brute efficiency. Exponential stretching dilutes curvature the way it dilutes unwanted relics, because curvature terms become negligible compared to the dominant vacuum-like energy. The flatness problem becomes a natural consequence of rapid expansion, not a delicate initial tuning. After enough e-folds, the geometry looks Euclidean on observable scales. The ball is no longer balanced. The hilltop has been stretched into a plane. Inflation is usually modelled with a high energy field and an effective potential, often called an inflaton for convenience. The field's energy density behaves like a temporary vacuum energy, with negative pressure arising from potential dominated dynamics. That negative pressure causes accelerated expansion in general relativity, because it contributes to the gravitational source term. In plain terms, the field acts like a spring held high on a hill, storing energy that drives expansion. The spring does not push matter outward, it changes how spacetime itself evolves. The details depend on the shape of the potential, which determines how long inflation lasts and how smoothly it ends. A flatter potential allows slow roll, where the field changes gradually and the vacuum-like behavior persists. A steeper potential ends inflation quickly, sometimes violently. These are not aesthetic choices, they affect observable predictions. Even the slight tilt in the primordial spectrum is a fingerprint of that shape. The model then needs inflation to end and reheat the universe, because an inflating vacuum is cold and nearly empty of particles. The field's energy must convert into a hot bath of particles and radiation through decay and interactions. This reheating sets the initial conditions for nucleosynthesis and later cosmic evolution, effectively lighting the furnace of the hot Big Bang. The universe becomes filled again, not by compression, but by conversion. On screen, the smooth stretching can give way to a sudden bloom of particles, like sparks filling a dark volume. Inflation is not only a smoothing machine, and this is where it becomes conceptually daring. It is also a generator of structure through quantum fluctuations, taking microscopic uncertainty and stretching it into macroscopic pattern. Tiny vacuum fluctuations in the inflating field and in the metric are stretched to cosmic scales. What begins as quantum noise becomes the blueprint for galaxies. The same randomness that seems like a nuisance in the lab becomes creative on the larger stage. In quantum field theory, even the vacuum is restless, with fluctuations constrained by the uncertainty principle. During inflation, wavelengths are stretched faster than causal processes can erase them. When a mode's wavelength exceeds the horizon, it effectively freezes, because causal microphysics cannot act across it. Those fluctuations become classical density perturbations after horizon exit, in the practical sense that they behave like fixed random fields. The quantum becomes a pattern not by magic, but by loss of causal contact. Later, when the universe expands more slowly, the perturbations re-enter the horizon and causal physics resumes. Gravity amplifies them into the scaffolding for galaxies and clusters, while pressure in the photon, baryon fluid, drives acoustic oscillations. The universe becomes a resonant instrument, and the CMB records the harmonics. The pattern is not arbitrary. It is a spectrum with peaks and troughs. Each peak is a timestamp of compression and rarefaction in the primordial plasma. This mechanism predicts a nearly scale-invariant spectrum of primordial perturbations, meaning fluctuations are similar across many length scales with a slight tilt. It predicts a specific pattern of acoustic peaks in the CMB power spectrum, corresponding to sound waves caught at different phases. It also predicts correlations that match what satellites like WMAP and Planck have mapped with exquisite precision. The data do not merely permit inflation, they often seem to speak its language. The fit is not just visual, it is statistical and parameter-rich. Inflation's success is therefore practical and quantitative, not only philosophical. It explains why the CMB is so uniform and why it is not perfectly uniform. It connects early quantum physics to the large-scale cosmic web, linking the smallest scales we can model to the largest structures we can observe. It is a bridge between the micro and the cosmic. Yet bridges invite the question of what lies on either side. Yet inflation is not a single theory with one clean set of parameters, and this is where confidence becomes cautious. It is a framework with many possible fields, potentials, and reheating histories. Different models can fit the same broad data with different microphysical stories. The umbrella is wide, and that width complicates the search for uniqueness. When many roads reach the same city, the map must be read carefully. That flexibility is a strength and a weakness, and the documentary lingers on the ambiguity. It allows inflation to survive many observational tests because it can be adjusted within a family of models. It also makes it harder to say what inflation uniquely predicts beyond general features, especially when new parameters hide in the reheating details. The more adaptable a framework becomes, the more carefully it must be constrained. Otherwise, explanation risks becoming accommodation. Some versions of inflation lead to eternal inflation, where inflation never ends everywhere, and the idea becomes almost vertiginous. Quantum fluctuations can keep parts of space inflating, while other parts reheat, creating a patchwork of outcomes. The result is a multiverse of bubble regions with different local conditions, separated by inflating space that keeps them apart. Our observable universe becomes one bubble among many. The camera can linger on a fractal-like foam, where new regions bud off as others cool. Eternal inflation raises a measure problem about probabilities, and it is not a technicality but a conceptual fault line. If infinitely many regions exist, counting outcomes becomes ambiguous, because every outcome happens infinitely often. Predictions can depend on how one regulates infinities and defines typicality, which risks turning physics into bookkeeping. The question becomes, what does it mean to say something is likely in an infinite ensemble? When probability loses its anchor, explanation becomes slippery. These issues do not erase inflation's empirical achievements, and they do not turn it into mere speculation. They show that inflation may be an effective description rather than a final explanation, a useful layer above deeper physics. The deeper question becomes what selects the inflating state in the first place, and why it began in the right conditions to start at all. The prelude itself demands a prelude. If inflation is the engine, what started the engine in the first place? At this point, the documentary's hook tightens. We began with a far future that may lose scale and clocks, drifting toward conformal simplicity. We now face a beginning that seems to require an astonishingly special starting point, not merely hot, but ordered in a particular way. The symmetry between end and beginning becomes a tension. It is as if the universe is easy to end, yet hard to start. The low-entropy puzzle is often stated too casually as a claim about smoothness and disorder, as if smooth automatically means random. In ordinary gases, smoothness looks like high entropy, because many microstates look uniform when averaged. A box of air at uniform temperature and density is a high entropy state, because there are countless microscopic arrangements consistent with that uniformity. With gravity included, that intuition flips, and the flip is the heart of the mystery. Gravity makes uniformity precarious rather than typical. In a gravitating universe, clumping increases entropy because gravity opens new macrostates. A smooth mass distribution is not the generic high entropy outcome, because gravity makes uniformity unstable. The generic outcome is structure, collapse, and eventually horizons, where information becomes hidden behind causal boundaries. Gravity turns smoothness into a special condition rather than a typical one. The same force that builds galaxies also builds the entropy budget. The early universe was hot and close to thermal equilibrium in matter and radiation, and that suggests high thermal entropy per particle. The photon bath had an enormous number of microstates, and the distribution was nearly perfect. Yet the gravitational field was extraordinarily ordered because spacetime curvature was unusually simple. Thermal disorder and gravitational order coexisted, and that combination is the clue. It tells us that entropy is not one number, but a bookkeeping across different degrees of freedom. This is why the CMB's smoothness is not a trivial equilibrium state, even though it looks like one at first glance. It is a sign that the gravitational degrees of freedom began in a very restricted configuration, with little room for tidal complexity. The arrow of time seems to be written into that restriction, as if the universe began with a boundary condition that favoured future growth of structure. We are not just explaining what happened, we're explaining why it could happen. Why did the universe begin with so much gravitational room still left to explore? Penrose frames the issue in terms of phase space volume and improbability, using the language of statistical mechanics. The set of initial gravitational states compatible with a smooth Big Bang is tiny compared to the set of allowed states, once gravity is included. The specialness is not a small detail, and it is not a mere aesthetic preference. It is the central boundary condition that makes an arrow of time possible. If the initial state were generic, the future would not look like our history. To make this vivid, the documentary might show a vast landscape of possibilities, with a narrow channel carved through it. Most gravitational configurations lead quickly to clumping, anisotropy, and horizons, which are high-entropy gravitational outcomes. The observed early universe sits in a rare corridor where the geometry is smooth enough to delay collapse. The question is why the universe began in that corridor, rather than in the overwhelming majority of alternatives. Is the corridor selected, or is it simply the one in which observers can arise? Inflation is often presented as a solution to smoothness, and in a limited sense it is. It can take a patch and stretch it, making it look uniform and flat, even if it began with modest irregularities. Penrose's objection is that inflation may move the problem rather than remove it, because it assumes an inflating patch that is already special. The mechanism smooths, but it also requires a smooth start. A smoothing machine still needs a surface to begin with. Inflation requires an inflating state that is itself special in gravitational terms, not merely energetic. It requires a region dominated by vacuum-like energy, with low inhomogeneity, so that accelerated expansion can proceed without being disrupted. The question becomes why such a region existed, why it was large enough, and why it began so smooth. If the inflating state is rare, then the rarity has not disappeared. The origin story shifts one step back, but it does not end. Penrose's deeper claim is that the real low-entropy condition is gravitational, not thermal, and he seeks a geometric diagnostic. He focuses on the Weyl curvature, the part of curvature associated with tidal distortions and the free gravitational field. A low Weyl curvature initial state corresponds to low gravitational entropy, because it suppresses the degrees of freedom associated with gravitational radiation and anisotropic distortions. In plain language, it means space-time began almost unwrinkled. The wrinkles are not in matter alone, but in the geometry itself. In the early universe, the Ricci curvature is tied to matter and radiation density through Einstein's equations. The Weyl curvature encodes anisotropy, shear, and gravitational radiation not fixed by local density, and it can exist even in vacuum. A nearly vanishing Weyl curvature means the geometry began with minimal tidal structure, like a calm ocean without swells. That calmness is not guaranteed by thermal equilibrium, and it is not demanded by the known dynamical laws. The equations allow many beginnings, yet we observe a remarkably quiet one. Penrose's Weyl curvature hypothesis proposes that the Big Bang had Weyl curvature near zero, and it treats this as a boundary condition. It sets the arrow of time by declaring that the universe begins in a state that strongly suppresses gravitational clumping and tidal complexity. The hypothesis does not claim to derive this condition from known physics, but it names the condition precisely. Naming the constraint is a way of sharpening the mystery. Once the condition is stated clearly, the demand for an explanation becomes harder to evade. As the universe evolves, Weyl curvature grows as structure forms, and the growth is visible in the sky. Inhomogeneities collapse, tidal fields strengthen, and gravitational radiation becomes possible as massive systems accelerate. The growth of structure then tracks a growth of gravitational entropy, even as local systems can temporarily decrease entropy by exporting heat. The arrow of time becomes a story of geometry becoming more intricate. The calm ocean develops currents, eddies, and storms. Black holes become the extreme case of gravitational entropy, and they make the abstract discussion concrete. Their horizon area encodes an enormous number of microstates in the Bekenstein, Hawking formula, where entropy is proportional to area in Planck units. A universe with black holes is a universe that has explored a vast region of gravitational phase space. The entropy budget becomes dominated by horizons, not by the thermal disorder of ordinary matter. On screen, the smooth early glow can dissolve into a later cosmos, punctured by dark silhouettes and lensing arcs. This is why the beginning looks so strange when compared to the end. The early universe contains almost no horizons and almost no gravitational complexity, despite its high temperature. The late universe contains many horizons and an enormous entropy budget dominated by them, even though it is cold and dilute. Heat is not the only measure of disorder, and gravity changes the accounting. The universe can cool while its entropy still climbs. The arrow of time then seems to depend on a special beginning rather than on dynamical laws alone. The second law explains why entropy increases from a low value, given such a value. It does not explain why the value was low to start with, and it does not specify which degrees of freedom were constrained. The universe appears to have begun with a rule about what kinds of gravitational complexity were allowed. The deepest question is not why entropy rises, but why it had room to rise. This is where CCC re-enters as a rival origin story rather than a poetic coda, and the narration shifts back to the boundary between aeons. CC claims the next Big Bang can be naturally smooth because the previous aeon's far future becomes conformally simple. If only massless degrees of freedom remain, scale loses meaning, and the boundary can be matched without a singular, jagged handoff. The end becomes a template for a new beginning. The story tries to close its loop using geometry rather than coincidence. In CCC, the end of one aeon is not a hot crunch but a cold, dilute limit, where the universe has expanded for an unimaginably long time. After black holes evaporate through Hawking radiation, the dominant gravitational structures disappear, and the remaining content is radiation-like. With no rest mass to set a scale, the geometry can be rescaled without changing causal structure. The conformal diagram becomes the key visual, with light cones preserved as the metric is stretched. The screen can show the same causal skeleton wearing different scales like different costumes. Penrose argues that this conformal boundary can enforce a low Weyl condition for the next aeon, and that is the conceptual payoff. The next Big Bang inherits a smooth gravitational state because the previous aeon ends without surviving tidal complexity. The arrow of time is then tied to a geometric matching rule, not to an unexplained initial miracle. The universe begins smooth because it ends smooth, in the conformal sense. A boundary condition becomes a bridge between eras, but the promise is also the vulnerability, and the documentary lets the doubt breathe. Does conformal rescaling truly remove gravitational entropy, or does it hide it by changing what counts as scale? If entropy is a count of microstates, a relabeling cannot by itself delete them, unless the relevant degrees of freedom genuinely disappear. The question becomes whether the late-time universe really forgets enough to reset the boundary. Forgetting is a strong claim in physics, and it demands a mechanism. CCC must therefore be judged as physics, not only as philosophical elegance, and the criteria are unforgiving. It must reproduce the empirical successes of the standard early universe story, because those successes are not optional. It must yield the observed CMB spectrum and anisotropies, the acoustic peak structure, and the near-scale invariant perturbations. It must do this without leaning on metaphor where equations are required. Beauty is welcome, but it cannot substitute for a fit. It must also yield the observed cosmic parameters that define our expansion history, because the numbers are now measured with precision. It must fit baryon density, dark matter abundance, and the effective number of relativistic species inferred from the CMB and nucleosynthesis. It must match the observed near flatness and the statistics of large-scale structure, including how clustering evolves over time. Any viable origin story must land on the same sky. The universe is not obliged to match our preferences, but our theories are obliged to match the universe. If CCC replaces inflation, it must provide another mechanism for generating the primordial perturbations, because the CMB's pattern is a quantitative fingerprint. If it coexists with inflation, it must explain what role the conformal matching plays that inflation cannot, and why both are needed. Either way, it must make contact with data rather than metaphor, because cosmology is now an observational science. The microwave background is not a canvas for ideas, it is a measurement. The sky is a dataset, and it is remarkably unforgiving. Inflation's fingerprints include specific correlations and polarization patterns in the CMB, and the documentary foreshadows what will matter later. Primordial gravitational waves would leave B-mode polarization at large angular scales, a twisting pattern distinct from density-driven E-modes. Non-Gaussianity constraints already limit many inflationary models, because the observed fluctuations are close to Gaussian random fields. The sky is not only mottled, it is statistically disciplined. Even the randomness has rules, and those rules are clues. CCCC's proposed fingerprints are different and more controversial, and the narration keeps the tone cautious. Penrose has argued for low-variance circles as possible imprints of violent events in a previous aeon, such as energetic processes associated with black holes. Critics argue these features are consistent with noise, selection effects, or standard statistics, and that the claimed signals are not robust. The debate is not about possibility alone, but about significance. In cosmology, significance is the difference between a hint and a discovery. The documentary does not decide the dispute here, because this chapter is about framing the problem with precision. It sets the stakes and clarifies what must be explained, whether by inflation, CCC, or something not yet imagined. A new origin story must earn its place by matching the sky we actually see, not the sky we wish to see. The universe is generous with beauty, but strict with evidence. If the beginning is special, the evidence of that specialness should be written somewhere. So we end this chapter with a sharpened tension. Inflation explains much, yet it may not explain the deepest specialness of the beginning, the low gravitational entropy that seems built in. CCC promises a geometric reason for smoothness, yet it must still reproduce the early universe data with quantitative fidelity. The beginning remains both illuminated and mysterious. We are left with a question that feels almost personal. Why did the universe start with such restraint? The next step is to look where the earliest information is preserved most cleanly, before stars and galaxies complicate the record. The place to look is the oldest light we can see, stretched into microwaves by cosmic expansion. We turn to the cosmic microwave background, and we ask whether it carries any echo of a prior aeon. We leave the philosophical edge of endings and step into measurement, because CCC lives or dies where predictions meet maps of the microwave sky. The shift is almost tactile. Ideas that sounded poetic now have to survive calibration tables, beam models, and the stubborn arithmetic of uncertainty. In cosmology, elegance is not enough, because a hypothesis must pass through detectors, pipelines, and the quiet tyranny of error propagation. The cosmic microwave background is our oldest photograph, but it is also a calibrated dataset with error bars attached. It was released when the universe became transparent, about 380,000 years after the Big Bang, at a time when matter and radiation finally stopped behaving like a single fluid. Before that moment, photons scattered off free electrons in a dense hot plasma, and information could not travel far without being scrambled. The early cosmos was not dark, but it was opaque, more like the interior of a star than an empty sky. In that plasma, pressure and gravity argued constantly, and the argument left a pattern we can still read. As the universe expanded, it cooled, and the average photon energy dropped until electrons could bind to nuclei and form neutral atoms. That transition, recombination, followed closely by photon decoupling, collapsed the scattering rate, and the mean free path of light suddenly became cosmic. Photons began free streaming, carrying a snapshot of temperature variations and gravitational potential wells imprinted across the last scattering surface. The surface is not a literal shell you could touch, yet it behaves like one in our maps, an ancient boundary drawn by atomic physics. Even the redshift is part of the story, because this light comes from around ZL100, when the universe was 1,000 times smaller. When we say oldest photograph, we also mean a photograph taken with a specific exposure time. The last scattering surface has thickness, because recombination happened over tens of thousands of years rather than in an instant. That finite duration blurs the smallest features, and it sets a physical limit on how sharp primordial patterns can appear. Even before we argue about CCC, the CMB already teaches a lesson. The universe records its history, but it records it with a known instrumental blur. In practice, that blur mixes with the telescope's own beam, so theory and hardware share responsibility for what looks sharp. Today that light is stretched into microwaves and fills the sky at about 2.725 Kelvin, a temperature colder than any natural place on Earth. Visually, imagine a dark dome of space, and then imagine that every direction glows with the same faint heat, like a uniform emberscape just above absolute zero. The spectrum is an almost perfect blackbody, a signature of early thermal equilibrium that was confirmed with extraordinary precision by Cope's Pheros instrument. Pheros did not just see microwaves, it measured a curve so exact that deviations would have rewritten early universe thermodynamics. Historically, that result mattered because it ruled out many messy alternatives, leaving the hot Big Bang picture with nowhere obvious to hide. That blackbody perfection is the calm surface, and the anisotropies are the ripples. The deviations from uniformity are tiny, at the level of tens of microkelvin, meaning 1 part in 100,000. Yet those tiny differences are not random noise in the everyday sense. They are structured by physics that can be written down and tested. They encode acoustic oscillations in the photon, baryon fluid, the baryon density that sets peak heights, and the dark matter content that deepens potential wells without adding pressure. They also encode the geometry of space, because curvature changes how a physical scale projects to an angular scale on the sky. In a visual sense, the peaks in the power spectrum are like harmonics from a drumhead, except the drum is the entire observable universe. The standard story treats these fluctuations as a statistically simple field, seeded by inflationary quantum fluctuations, stretched to astronomical scales. In that picture, the pattern is close to Gaussian, meaning its information is largely contained in the two-point correlation function, or, equivalently, the angular power spectrum. The familiar plot of CMB peaks is not decorative. It is a compressed fingerprint of the universe's composition and expansion history. A single curve extracted from a full sky map can tell you the age of the cosmos, the baryon fraction, and the amplitude of primordial perturbations. What looks like a smooth line is actually a treaty between many parameters, each constrained because the peaks shift together in predictable ways. But CCC asks whether the CMB carries more than the story of this eon. If one aeon's remote future is conformally matched to the next aeon's beginning, some violent late events might survive as scale-free imprints. The claim is not that galaxies cross the boundary, or that stars drift intact into a new beginning, because masses lose meaning under the conformal rescaling CCC relies on. The claim is subtler. Patterns carried by radiation, and by the geometry that guides radiation, could persist when the universe is reinterpreted through a conformal lens. The question is almost cinematic. Can the closing credits of one cosmos leak into the opening scene of the next? In CCC, the far future is dominated by radiation and effectively massless degrees of freedom, because massive particles either decay, are swallowed, or become irrelevant compared with the stretching of spacetime. That assumption matters, because conformal transformations preserve angles and light-like structure, while washing out absolute scales. It is a mathematical way of saying that if everything becomes light-like enough, the end can be redescribed as a beginning. The observational question becomes narrow and brutal, because mathematics alone is not evidence. Are there statistically significant features in the CMB that look like echoes, not just random fluctuations? If the sky's a record, we have to ask whether it is a diary or a palimpsest. CCC proponents focus on a proposed signal called Hawking points, which are meant to be sharp enough to search for. In this framing, supermassive black holes in the previous Asyon evaporate through Hawking radiation, an effect where quantum fields near the horizon produce particle emission. For stellar mass black holes, that evaporation time is fantastically long, far beyond the current age of the universe. For supermassive black holes, the timescale is longer still, so the idea implicitly lives in a remote cosmic future where ordinary astrophysical clocks have run out. The mechanism is conceptually simple, but physically extreme, because it depends on horizons behaving like thermodynamic objects. Near the end of evaporation, the remaining mass is released as a burst that is extremely energetic in its own frame. Because the temperature of Hawking radiation rises as the black hole shrinks, CCC arguments then invoke conformal mapping, claiming that this final burst can be re-expressed as an injection into the next aeon's early radiation field. The imprint would appear as a localized hotspot in the CMB, with an angular scale set by the mapping and by how the disturbance propagates before recombination. In narration terms, it is a message written in heat, small, circular, and placed on a sky that otherwise looks statistically indifferent. Visually, it is like finding a single warm pinprick on a globe of near-uniform frost. The Hawking point idea tries to be specific about morphology, because specificity is what makes it testable. The spot should be compact and roughly circular, not a random filament that could be blamed on scanning artifacts. It should have a temperature profile that falls away from a center in a predictable way, like a gentle hill rather than a jagged spike. It should be rare enough to stand out from Gaussian fluctuations, yet common enough to be found in full sky data without cherry-picking a single example. Its distribution should not track the Milky Way or known foreground structures, because a cosmological echo should not care where our galaxy happens to be. And if the signal is truly primordial, it should not prefer one observing frequency over another, once foregrounds are removed. A useful visual here is to imagine the CMB map as a mottled sphere, blue and red speckles spread across a globe. Then, somewhere within that speckle field, you search for a slightly brighter dot with a smooth radial fade, as if a pebble had been dropped into a pond long ago. The difficulty is that Gaussian random fields also produce peaks, and some peaks will look smooth simply by chance. CCC is therefore asking the map to do something subtle, not merely contain hotspots, but contain hotspots with the right statistics and the right profile. The challenge is psychological as well as mathematical, because our eyes are trained to promote coincidence into meaning. CCC also inspired earlier claims of concentric low-variance circles, which sound almost like a target pattern stamped onto the sky. The proposed origin is different, but the logic is similar, because it again relies on a violent event in the previous aeon. A supermassive black hole merger could produce an expanding burst of gravitational radiation, a wavefront that carries energy outward at the speed of light. After conformal matching, that burst becomes a spherical disturbance in the early plasma, and when projected onto the last scattering surface, it could appear as a circle. Multiple events from the same region, or repeated episodes, could produce multiple concentric circles with a shared center. On screen, the idea is instantly legible, rings on a cosmic globe, yet the statistics behind ringness are where the real fight begins. The concentric circle claim makes a statistical promise, and it is a promise that can be checked. Along certain rings, the temperature fluctuations should have unusually low variance compared with typical rings of the same radius. The effect should persist under changes in resolution and masking, because a real physical imprint should not vanish when you rebin pixels. It should not be an artifact of how the sky is scanned, or how the map is filtered, because those artifacts often leave telltale alignments with the instrument's motion. If real, it would point to a pre-Big Bang influence that inflation does not predict in its simplest forms. The deeper issue is whether the anomaly is local, like a scar, or global, like a change in the rules. A third family of anomalies is more diffuse and more controversial, partly because it is easier to argue about them without ever agreeing on a single test. Some analyses point to unusual alignments in low multipoles, including the so-called axis of evil, where large-scale modes appear to line up in a way that feels aesthetically suspicious. Others note hemispherical power asymmetry, where one half of the sky seems slightly more active than the other. Still others focus on the cold spot, an unusually large region of lower temperature that invites both cosmological and mundane explanations. These are the features that thrive in the borderland between statistics and storytelling, because they are visible enough to tempt us and broad enough to resist closure. CCC does not uniquely predict these patterns, but they are sometimes discussed as hints that the sky is not perfectly statistically isotropic. The danger is that anomalies can be collected like souvenirs, each one weak, together sounding persuasive. The mind is excellent at building a narrative from coincidences, especially when the sky offers only one realization to look at. A question hangs in the background. Are we seeing a message, or are we seeing the human habit of finding faces in clouds? If the universe hands us a single map, how do we separate an imprint from an impression? To evaluate any of these claims, we need to understand what the CMB maps actually are, because the photograph is not a direct image. Satellites do not measure temperature directly at each point on the sky, as if they were taking a simple snapshot. They measure microwave intensity in multiple frequency bands while scanning in time, recording voltages that must be converted into sky brightness. Mapmaking turns time-ordered data into a sky map by solving for pixel values that best fit the scan pattern and instrument model. Every step introduces choices, some explicit, some hidden in software defaults, that can imprint subtle systematics. Even the definition of zero level matters, because the monopole is removed and only differences remain. Historically, the path from raw signal to cosmological map was itself a triumph. Cope first detected the anisotropies at large scales, then UMAP mapped them with much finer detail, and Planck pushed further with higher resolution and broader frequency coverage. Each mission brought its own scanning strategy, thermal environment, and instrument design, and each had to fight the same enemy: tiny signals buried under much larger foregrounds and instrumental noise. When CCC asks for faint imprints, it is asking us to trust that this entire pipeline is not inventing patterns. The history also matters because each generation learned from the last, tightening systematics that once looked like unavoidable fog. Foreground removal is the first major battleground, because the microwave sky is not empty. The Milky Way emits microwaves through synchrotron radiation from electrons spiraling in magnetic fields, which tends to dominate at lower frequencies and carries a polarized signature. It emits free radiation from ionized gas, produced when electrons scatter off ions without being captured. It emits thermal dust emission from warm grains, which rises at higher frequencies and can look like a glowing veil draped across the galactic plane. Extragalactic sources add radio galaxies, quasars, and infrared emitters, each contributing point-like or clustered contamination. In a visual montage, these foregrounds are like translucent weather systems sliding over the same globe, each with its own texture and color. Each component has a different frequency dependence, so multi-frequency observations allow separation, but never perfectly. In an ideal world, you could decompose the sky like a set of transparent layers: synchrotron, dust, free, and the underlying CMB, and peel them apart cleanly. In reality, spectral indices vary across the sky, dust temperature changes with environment, and instrument bandpasses are not identical to their nominal labels. Foreground cleaning becomes a sophisticated inference problem, not a simple subtraction. Even small mismatches can leave residuals that are coherent across degrees on the sky, which is exactly the scale where CCC searchers like to live. Different teams use different component separation pipelines, and that diversity is both a strength and a source of disagreement. Some fit parametric models for foreground spectra, estimating spatially varying parameters and propagating uncertainties. Others use blind methods like internal linear combination, which minimize variance under constraints but can inadvertently suppress real CMB features. Each method trades bias against variance, and each can leave residuals that are small in amplitude yet structured in shape. Residual foregrounds can masquerade as spots, rings, or alignments if they correlate with the scan strategy or with mask edges. The uncomfortable truth is that cleaned never means pure, it means best effort with quantified leftovers. A claimed CCC signal must survive analysis choices that were not tuned to find it, because tuning is where false positives quietly breed. If a hotspot is only significant in one particular cleaned map, that is a warning sign. If concentric circles appear only after a specific filtering step, that is another warning sign. The CMB is a delicate dataset, and delicate datasets punish overconfidence. The more spectacular the claim, the more ordinary the explanation must be ruled out. Masking is unavoidable because the galaxy is bright and messy, especially near the plane where dust and synchrotron flare. Analysts remove the dirtiest regions of the sky, then infer statistics from the remaining clean fraction. But masks create sharp boundaries that couple modes and distort ring statistics, because the spherical harmonics no longer remain orthogonal on a cut sky. A ring that crosses a mask can have artificially reduced variance if contaminated pixels are removed unevenly. A hotspot near a mask edge can be amplified by filtering choices, turning a mundane residual into something that looks like a deliberate mark. In other words, the very act of hiding contamination can sculpt the statistics you later celebrate. There is also a visual reality to masking that matters for narration. On screen, the full sky map becomes a globe with a thick grey band cut out, like a censored strip across the Milky Way. The remaining sky looks pristine, but it's no longer the whole sky, and statistics derived from it must account for what was removed. The sky is not only a dataset, it is a dataset with missing data, and missing data always complicates inference. When we ask whether the universe wrote a circle, we must also ask what parts of the page we tore away. After cleaning and masking, scientists compare the real sky to simulated skies, because significance is a comparative concept. The baseline is LCDM plus inflation, with parameters fixed by best fits to the CMB itself and to related datasets. Simulations include beam smoothing, anisotropic noise, and the scan pattern, so the mock maps resemble the data in the ways that matter for the test. Analysts then run the same search algorithm on both real and simulated maps, producing a distribution of outcomes under the null hypothesis. The key output is a p-value, the fraction of simulations that produce something at least as extreme as the data. This is the stage where intuition often fails, because rare depends on the rules of the game you actually played. This is where the look elsewhere effect becomes decisive, because the sky offers many places to look and many ways to define extreme. If you search the sky for any unusual circle, you can vary center, radius, thickness, and the statistic used to measure variance. If you search for any hotspot, you can vary smoothing scale, threshold, and profile shape, and you can decide whether to weight pixels by noise. With enough trials, random Gaussian maps will produce seemingly special features, including features that look eerily clean to the human eye. The sky is large, and the space of possible questions is even larger. The correct question is not whether a feature exists, because features always exist in a rich random field. The correct question is whether it is unlikely given the entire search procedure, including all the knobs you turned along the way. A procedure that tries many possibilities must pay a statistical price, because each additional possibility is another chance to fool yourself. CCC searches often live or die on whether that price was paid honestly. In practice, that means counting not just the final test, but the exploratory steps that led you to it. Accessible language helps here, because the logic is simple even when the math is not. If you roll a die once and get a 6, that is mildly surprising. If you roll it 1,000 times, a 6 is guaranteed somewhere, and surprise is misplaced. In CMB searches, the number of effective rolls can be enormous. Because the parameter space is large and because the sky has many pixels, a posteriori choices, made after seeing the data, silently increase the number of trials, even when the paper's headline number does not reflect it. The deeper question is almost ethical. When does curiosity become a claim? That inflation of trials can turn noise into a headline, and it can do so without anyone intending to cheat. Scientists are human, and the temptation to refine a search after seeing an intriguing feature is almost automatic. Yet the difference between exploration and confirmation is the difference between curiosity and evidence. CCC, because it deals in subtle patterns, is especially vulnerable to this boundary. The more flexible the method, the more it can discover what it was built to admire. Many critiques of CCC signal claims focus on this statistical accounting, and the critiques are often technical rather than rhetorical. Some argue that the reported circles or Hawking points were selected after scanning many possibilities, which makes their quoted significance too optimistic. Others show that similar features appear in LCDM simulations when the same filters are applied, suggesting that the method itself manufactures apparent structure. Some find that significance drops when using alternative masks or component separation maps, implying that the effect is not stable. The dispute is not only about one number, but about whether the test was defined before the data were inspected. In a field built on one sky, procedural rigor becomes a substitute for repetition. Instrumental systematics add another layer, because real telescopes are not ideal. Duller map and Planck have different beams, noise properties and scan strategies, and those differences matter when you hunt for compact features. A real cosmological feature should appear in both datasets, within expected differences in resolution and noise, but subtle beam asymmetries can create ring-like artifacts around bright sources, especially when scanning repeats along preferred directions. Time domain filtering can imprint stripes or correlated noise that affects variance statistics, leaving patterns that are not cosmology, but are also not obviously instrumental, without careful modelling. The instrument in a sense has its own handwriting. A robust detection must be stable across instruments and across map-making choices, and that stability is a high bar. It must survive different treatments of 1F noise, different de-stripping algorithms, and different assumptions about gain calibration. It must also survive different choices of pixelization and smoothing, because small-scale features can be sensitive to how the map is gridded. When CCC claims a specific morphology, it is implicitly claiming that morphology is not an artifact of these steps. The burden is heavy because the claimed signals are small, and small signals live where systematics like to hide. Polarization can help, but it also complicates, because polarization is weaker and more foreground contaminated than temperature. Temperature anisotropies are dominated by scalar density perturbations, while polarization encodes scattering geometry and velocity fields at last scattering. In simple terms, polarization is produced when electrons see a quadrupole pattern in incoming radiation, so it carries information about local motion and anisotropy. A CCC imprint that perturbs the early plasma might have a correlated polarization signature, and that correlation could serve as a cross-check. Visually, polarization maps look like tiny directional strokes painted over the temperature modelling. Subtle, but potentially decisive. If a hotspot is truly primordial, it may align with specific E-mode patterns, because temperature and E-mode polarization are statistically linked in LCDM. If it is a foreground or noise artifact, polarization correlations may fail, or the signal may appear only in frequency bands where dust polarization is strong. The promise is powerful. A temperature-only anomaly can be ambiguous, but a match temperature, polarization pattern is harder to fake. The complication is equally real. Polarization maps have their own systematics, and the cleaning problem becomes even more delicate. The sky offers a second channel of evidence, but it also offers a second channel of mistakes. So what would count as strong evidence for CCC in the microwave sky? Beyond intriguing pictures and selective statistics, the first requirement is a pre-registered prediction, stated before looking at the relevant data, because pre-registration forces discipline. It must specify the statistic, the angular scale, the expected profile, and the expected abundance, rather than leaving them adjustable. It must also specify how foreground cleaning and masking are handled, because those choices can move the result. Vague predictions invite flexible searches and flexible interpretations, and flexibility is the enemy of significance. In a mystery, ambiguity is atmosphere, but in a measurement it is a loophole. The second requirement is independence of pipelines, because a real signal should not depend on one team's favoured method. The same signal should appear in maps produced by different component separation methods, including ones designed with different assumptions. It should persist under reasonable changes in mask and resolution, and it should not vanish when you slightly alter the ring thickness or the smoothing kernel. It should be detectable by teams not invested in CCC, using code written independently, because replication matters more than rhetoric when the sky is only observed once. Agreement across rival methods is the closest thing cosmology has to a rerun. The third requirement is model comparison, not only anomaly counting, because science is not a contest of oddities. A feature can be unusual under one statistic yet still not improve the overall fit of a cosmological model. CCC must provide a likelihood that competes with LCDM, not just an explanation after the fact that sounds satisfying. If adding CCC parameters improves fit only by overfitting, Bayesian evidence will penalize it, because extra freedom is not free. The goal is not to tell a better story, but to predict more with fewer degrees of freedom. A model should earn its complexity by paying it back in explanatory power. Even a clean CMB signature would not be enough by itself, because cosmology is now a web of linked measurements. Any cosmological model must be globally consistent with the rest of precision cosmology, not merely compatible with one mapped feature. The same initial conditions that shape the CMB also shape the matter power spectrum because they seed the growth of structure. They affect how galaxies cluster, how gravitational lensing distorts background light, and how baryon acoustic oscillations appear in surveys. A model that explains one anomaly but breaks 3 other datasets is not a viable origin story. The universe does not let you edit one chapter without changing the rest of the book. Large-scale structure provides a hard check because it traces the growth of the same primordial perturbations over billions of years. The amplitude and scale dependence of fluctuations are measured in galaxy surveys and weak lensing maps, and those measurements can be compared to CMB-inferred predictions. BO provides a standard ruler tied to the sound horizon, which is also encoded in the CMB peaks, linking early universe physics to late-time geometry. CCC must reproduce these linked scales without smuggling in inflationary assumptions it claims to replace, because hidden assumptions would hollow out the claim. Consistency across probes is the price of admission, and it is a price that cannot be negotiated away. Gravitational lensing of the CMB itself adds another constraint, because the CMB is not only a relic surface but also a backlight. Planck measures the lensing potential power spectrum, which depends on matter distribution integrated along the line of sight. Lensing subtly smooths the acoustic peaks and converts some E-mode polarization into B modes, offering an internal consistency check. If CCC changes the primordial spectrum or introduces localized features, it can alter lensing statistics in ways that are already tightly bounded. The CMB in this sense is both the message and the light by which we read later structure. Any claimed Hawking point population must not create lensing or secondary anisotropies that are already ruled out, including distortions from rayonization, the Sunyaev-Zeldovich effect, or unresolved point sources. The microwave sky is not only a surface of last scattering, it is also a record of everything that happened later, layered on top of the primordial pattern. A localized hotspot must be distinguished from a late-time imprint, and that is harder than it first appears. The universe writes with many pens, and the CMB is where their ink overlaps. The question becomes whether the mark is ancient or merely a smudge from a later page. At this stage, the documentary's tension sharpens, because the idea is haunting and the data are unforgiving. CCC offers a possibility that the universe's final darkness becomes a new beginning, and it offers a concrete place to look for traces. The CMB is the one place where that possibility could leave a measurable mark, because it is the earliest electromagnetic signal we can observe directly. Yet the same dataset is a minefield of statistics, foregrounds, and human pattern finding, and it punishes anyone who confuses fascination with inference. The mystery remains, but it is a disciplined mystery, fenced in by what the instruments can actually justify. The difference between an echo and a coincidence can hinge on how the question was asked, and on how many questions were asked before that. A circle can look like a circle because the universe put it there, or because the algorithm was designed to find circles in anything. A hotspot can look like a burst from another aeon, or like a perfectly ordinary peak that happened to be smoothed at the right scale. When the signal is subtle, methodology becomes part of the story. The plot is not only in the sky, it is in the way we interrogate the sky. We can now state the controversy cleanly, without either dismissing it or romanticizing it. CCC-inspired features have been reported, but many independent analyses find them consistent with LCDM expectations once the full search procedure is accounted for. Some signals weaken when correcting for look elsewhere effects, and that weakening is exactly what statistics predicts when you search widely. Some depend on particular smoothing scales or masks, which suggests sensitivity to analysis choices rather than to physics. Some resemble artifacts that appear when scanning a Gaussian random field for rare patterns, because rare patterns are guaranteed somewhere. The sky is generous with coincidences, and it charges interest when we borrow them for meaning. The debate remains unsettled largely because the proposed signals are subtle, and the search space is large, and because subtlety invites disagreement. One team may define the statistic one way, another may define it slightly differently, and the significance can swing. One team may trust one component separation map, another may trust a different one, and the candidate features shift. In this kind of controversy, The most important question is not who is right, but what would make everyone agree. The answer is rarely a louder argument, and almost always a cleaner test. This does not mean CCC is disproven, and it does not mean the standard model is complete, because incompleteness is part of honest science. It means the observational arena is unforgiving, and the burden of proof is high, especially for claims that reach beyond the standard narrative. If the universe really carries messages across aeons, those messages must survive our instruments and our biases. They must be clear enough to rise above a sky that is already rich with structure, and they must not dissolve under replication. A true signal should look less like a clever find and more like an unavoidable conclusion. They must also fit into a cosmology that works everywhere else, because the universe does not grant exceptions for beautiful ideas. A model that changes the earliest conditions must still produce the right abundance of galaxies, the right pattern of lensing, and the right BAO scale. It must also preserve the successes of LCDM where LCDM is strong, because replacing a theory means inheriting its responsibilities. CC, if it is to be more than a metaphor, must meet that standard. The romance of cyclic time has to cash out in numbers. One sentence becomes the chapter's hinge, because the documentary has to move forward without pretending the data are clearer than they are. If the data remain ambiguous, the next battleground is theory, where geometry meets quantum physics in the most extreme objects we know. The story narrows from the whole sky to the darkest points in it, because CCC's most dramatic proposed signals come from black holes. The camera, in effect, zooms from a mottled sphere to a horizon so small it can hide a paradox. Hawking radiation is quantum field theory on curved spacetime, not a fully unified theory, and it sits exactly on the fault line CCC wants to cross. It treats the spacetime background classically, as general relativity describes it, while quantizing fields that live on that background. The result is profound and unsettling. Black holes are not perfectly black, and horizons have a temperature, yet the end state of evaporation raises questions about information, unitarity, and what is lost behind horizons, questions that remain open in quantum gravity. Historically, this is where 20th century physics began to argue with itself, because thermodynamics, relativity, and quantum theory all insist on being taken seriously. If CCC needs black holes to write messages into the next aeon, we must understand what black holes can actually emit and what they can preserve. Can a final burst carry structured information, or is it effectively thermal noise? Can a conformal mapping transmit more than energy, or does it wash away the very details CCC wants to keep? These are not decorative questions, because the observational claims depend on the theoretical mechanism being physically coherent. If the mechanism cannot carry a pattern, then the sky cannot be expected to display one. We close with the documentary's hook in a new register, leaning into mystery without abandoning discipline. What if the universe's final cold breath is not silence, but a faint transmission, one that arrives as a subtle warmth on the oldest light we can see? The microwave sky is where we would first notice it, and it is where we first learn how hard it is to be sure. Now we turn to the engine room of the idea, where the fate of information may decide whether aeons can touch. The next step is not a prettier map, but a harder question. We transition from maps to mechanisms, from statistics to the physics of horizons, because the next step is no longer about circles on a sphere. The next chapter follows the trail into black holes, quantum gravity, and the meaning of an ending that might still remember. We have followed the microwave sky to the edge of a claim. Now we descend into the physics that would make an echo possible. CCC leans on a specific promise, and it is a daring one. The universe's final darkness might be a boundary, not a dead end. In that picture, the far future is not merely empty space cooling forever. It is a surface where one description of spacetime gives way to another. That promise runs through black holes, because black holes are the last engines left after stars fade. When galaxies exhaust their fuel, when stellar nurseries go quiet, gravity still keeps a ledger. It gathers remnants, merges them, and leaves behind horizons that can outlast almost everything else. To see why CCC cares, we have to slow down and look at what a horizon really is. In general relativity, a horizon is simple in definition and brutal in consequence. It is a surface that divides causal access, so that signals from one side can never reach the other. Visually, a horizon is not a wall you could touch. It is a boundary drawn by light itself, by the paths that photons can and cannot take. In a spacetime diagram, it is the line where future-directed light rays just fail to escape. Yet the classical story is only half the story, because the universe is quantum at every scale. In quantum field theory, the vacuum is not empty, even when no particles are present. It is a state with fluctuations and correlations, a restless baseline that cannot be made perfectly still. Those fluctuations are not optional noise. They are enforced by commutation relations and uncertainty, and they are measurable in subtle ways. The Casimir effect, for example, shows that even nothing can push on metal plates when boundary conditions change. Put quantum fields together with curved spacetime and the horizon becomes active. Particle creation appears where classical intuition expects silence. The horizon acts like a kind of amplifier, converting vacuum correlations into real excitations for distant observers. Hawking's result is often told as a particle escaping from inside, but that picture misleads. It is not a classical object tunneling out of a prison. It is a mismatch in how different observers define the vacuum, because time itself is sliced differently near a horizon. Near the horizon, field modes are stretched and mixed by gravity, and the stretching is extreme. Wavelengths that were once microscopic are dragged outward, and their phase relationships are scrambled. Positive and negative frequency components no longer align globally, so no particle in one frame becomes particles in another. One way to say it is pair creation near the horizon, with one partner falling in and one escaping. Another way is Bogoliubov transformations between past and future modes, which is the precise language of quantum fields in changing backgrounds. Either language points to the same outcome, and the outcome is startlingly concrete. The outgoing radiation looks thermal to distant observers, as if the black hole has a temperature. It is not a metaphorical temperature, and it is not a property of the interior. It is an effective temperature associated with the horizon's surface gravity, the acceleration needed to hover just above it. Surface gravity is a geometric quantity, and it measures how sharply spacetime is curved at the horizon. Stronger surface gravity means a hotter horizon and a more intense flux of radiation. In the simplest case, the temperature is proportional to surface gravity, divided by Planck's constant and the speed of light. For a non-rotating, uncharged black hole, temperature scales inversely with mass. Large holes are cold, small holes are hot, and the scaling is unforgiving. A stellar mass black hole radiates at a temperature far below the cosmic microwave background today, so it gains energy rather than loses it. This is why evaporation is slow at first, and for many black holes it is effectively frozen. A supermassive black hole radiates feebly for unimaginable times, with a temperature so tiny it is almost a mathematical whisper. Only when the universe itself cools below that temperature does net evaporation become possible. As mass decreases, the temperature rises, and the power output increases. The shrinkage accelerates because the radiating area decreases more slowly than the temperature increases. In simple estimates, the luminosity scales roughly like 1 over mass squared, so the endgame is not gentle. The late stage becomes a runaway, at least in the semi-classical story. The remaining mass is lost faster because the horizon grows hotter as it contracts. The black hole's lifetime scales like mass cubed, which means the last fraction of mass disappears in a comparatively brief finale. This accelerating end is central to CCC's imagery, and it is easy to see why. A final burst could be the last energetic act of an aeon, a brief flare after eons of dimming. In a visual sequence, the black hole would shrink from a silent shadow into a tiny, bright ember. Yet the details matter, because CCC is not only telling a dramatic story. The spectrum is nearly thermal, and thermal radiation is information poor in a naive reading. A perfect blackbody curve carries little about the specific history of what formed the black hole. CCC wants late-time energy release to seed a localized imprint, not merely a uniform bath. The CMB searches for Hawking points depend on that mapping from a final burst to a specific pattern. The question is whether the physics can naturally produce a concentrated, recognizable signal. Even in standard calculations, thermal is not the same as featureless. Greybody factors modify the spectrum because the curved spacetime outside the hole scatters outgoing modes. Rotation, charge, and environmental fields can also shape what escapes, although the broad thermal character remains. But Hawking radiation is derived semi-classically, and that is a controlled compromise. The spacetime is treated as classical while fields are quantized, which is consistent when curvature is mild compared to the Planck scale. For large black holes, the horizon curvature is tiny and the approximation is excellent. It becomes questionable near the end when curvature approaches Planck scales and quantum gravity should dominate. The semi-classical treatment assumes a smooth background, but the background itself is now fluctuating, so the first tension appears, and it is not a minor technicality. CCC needs the last stage to be meaningful, while our tools become least trustworthy there. The very regime where a dramatic burst could occur is also the regime where we cannot rely on the standard derivation. That does not refute the idea, but it makes it conditional on unknown physics. The second tension is deeper, and it has haunted theoretical physics for decades. It is the black hole information problem, which is not about human knowledge. It is about whether quantum mechanics remains self-consistent when horizons form and evaporate. Quantum theory demands unitarity, which means probabilities add up and pure states evolve to pure states. Information, in the technical sense, is not destroyed by time evolution. If it were, quantum mechanics would need a new rule, and that would ripple through every domain of physics. Hawking's original calculation suggests thermal radiation, and thermal radiation seems to erase the details of what fell in. If the outgoing state is exactly thermal, it is mixed, and it carries no record of the initial pure state. If a black hole evaporates completely, where did the information go? The question is not philosophical, it is a consistency test. If information can vanish behind a horizon and never return, then quantum evolution is not unitary for observers who remain outside. That would be a profound change, and it would demand a new framework beyond standard quantum theory. The paradox sharpened because black holes have entropy, and that entropy is enormous. Bekenstein argued that a black hole's entropy should scale with its area, not its volume, because otherwise the second law could be violated. Hawking's calculation then fixed the proportionality constant, tying entropy directly to horizon area in Planck units. Entropy counts microstates, even if we do not yet see them explicitly. If a black hole has microstates, evaporation should reflect them somehow, at least in principle. Otherwise, the entropy would be a bookkeeping trick rather than a physical count. Historically, this problem reshaped quantum gravity research. It pushed physicists toward holography, toward the idea that gravitational degrees of freedom might live on boundaries. It also forced a rethinking of locality, because the horizon seems to scramble information in ways that ordinary quantum field theory does not anticipate. The modern view has shifted, and the shift is not purely aesthetic. Many physicists now expect evaporation to be unitary, meaning the radiation ultimately encodes what fell in. The challenge is to explain how that encoding happens without violating the equivalence principle at the horizon. Holography is one reason for this confidence, and it comes with a powerful example. In anti-de Sitter space and related settings, gravity can be equivalent to a boundary quantum theory. The boundary theory is manifestly unitary, so the bulk process, including black hole formation and evaporation, should be unitary as well. That correspondence is not our universe in detail, but it is a proof of concept. It shows that quantum gravity can, at least in some worlds, preserve information. It also suggests that spacetime geometry might be emergent from entanglement patterns in a deeper theory. The Page curve is another reason, and it turns the paradox into a quantitative target. If evaporation is unitary, the entanglement entropy of the radiation should rise at first, then fall after the Page time. Early radiation is entangled with the remaining black hole, but late radiation must purify the early radiation. Hawking's semi-classical picture predicts only rising entanglement, because each emitted quantum appears entangled with a partner behind the horizon. That monotonic rise implies information loss if the black hole disappears. The Page curve therefore became a diagnostic, a way to test proposed resolutions. Recent work with islands changes the semi-classical bookkeeping in a surprising way. It adds new saddle points in gravitational path integrals, and those saddles effectively enlarge the region that counts as part of the radiation's entanglement wedge. In plain terms, the calculation learns to include parts of the interior when computing the entropy of the exterior radiation. With islands, the Page curve can emerge, consistent with unitarity. The radiation's entropy eventually decreases, as if the interior information is being transferred out. The result is technical, but its implication is simple. The semi-classical story was missing contributions that become important after long times. This is a shift with narrative consequences, because it changes what evaporation means. Evaporation may not be featureless thermal noise after all. even if it looks thermal in coarse measurements. The information could be hidden in subtle correlations, distributed across the radiation in a way that is hard to decode. But it also complicates CCC, because CCC often speaks as if black holes erase gravitational complexity. The Weyl curvature can be drained when horizons vanish, leaving behind a smooth, low-structure end state. If evaporation is unitary, the information is not destroyed, it is redistributed. Then the end state is not simple in an absolute sense. It may be simple only in coarse-grained thermodynamic variables, like energy density and temperature. Under the hood, the radiation could carry an intricate pattern of entanglement, a fossil record written in correlations rather than in lumps of matter. CCC needs a specific kind of simplicity, and it is more demanding than low energy density. It needs scale to lose meaning, not merely energy to spread out. It needs the universe to approach a regime where only angles and light cones matter, and where masses no longer define preferred rulers. So we ask what survives at the end, and the question becomes concrete. Does the universe become effectively massless, not just cold and empty? In CCC, mass is the enemy of conformal matching, because mass sets a scale through Compton wavelengths and rest energy. A massive particle carries a built-in clock, even if it is alone in deep space. Its rest mass defines a frequency, and that frequency defines a timescale. If masses persist, then scale persists in principle, and conformal invariance is not exact. If all particles are massless, physics becomes conformally invariant in a practical sense. Only light cones remain meaningful, because null directions are preserved under conformal rescaling. The difference between a meter and a kilometer becomes a matter of convention rather than a physical distinction. How could a universe lose mass, and lose it for good? There are several routes, and none are settled, but each route has a distinct scientific flavour. Some are particle physics hypotheses, and others are astrophysical processes that play out across absurd spans of time. Proton decay is one route, and it has a long history in grand unification. Many grand unified theories allow baryon number violation, which would make protons unstable. Experiments have not seen it, but the lower bounds on the lifetime still permit decay on timescales far beyond the current age of the universe. If protons decay, baryonic matter dissolves into lighter particles such as positrons, photons, and neutrinos. Chemistry ends, then solids end, and eventually even isolated atoms become impossible. The timescale could be enormous, but finite, and it would remove a major reservoir of rest mass. Even without proton decay, electrons can be removed from ordinary matter over long times. Capture into compact objects is possible, especially as stellar remnants and black holes interact gravitationally. In the deep future, rare encounters become the dominant events, and a single close pass can change a system's fate. Black holes can swallow stray particles, and they do not need much help. Gravitational encounters and slow accretion could feed remnants into horizons one by one. Over times far longer than the current cosmic age, even improbable captures can accumulate into a significant effect. In the far future, most bound structures are disrupted because gravitational systems are not perfectly stable. Encounters eject objects or send them inward, and the slow dance of three-body interactions tends to fling one participant away. Galaxies thin out, star clusters evaporate, and the universe becomes a sparse archipelago. If black holes dominate, they become sinks for rest mass, and CCC then waits for Hawking radiation to return that energy as light. The idea is thermodynamic and geometric at once. Mass is converted into radiation, and radiation is the form of energy that respects conformal symmetry. But there is a hard counterpoint, and it cannot be ignored. Some massive particles might be stable forever, and even a small relic population could matter. The electron appears stable, and its stability is supported by charge conservation and the absence of lighter charged particles. Neutrinos have mass, and their stability is strongly expected because there is nothing obvious for them to decay into. Even a tiny neutrino mass is still a mass scale, and it persists as a feature of the laws. Dark matter might also be stable, because many candidates are designed to be long-lived on cosmological timescales. If stable massive particles persist, the universe never becomes truly massless. Conformal invariance would be broken in principle, even if the breaking is operationally hard to detect. A mass scale can anchor physics, because it provides a reference that does not dilute away. CCC can respond by arguing operational irrelevance, and the argument has a certain austere logic. If everything is so dilute that masses cannot form clocks, scale may still fade from what any physical process can measure. In that limit, the universe could behave as if it were massless, even if masses exist in the equations. Yet that response is not automatic, and it raises a subtle question. A single stable mass scale can anchor physics, even in a thin universe, because it can define a threshold for reactions and a characteristic wavelength. The question becomes whether mass disappears physically or only becomes unmeasurable. CCC needs the stronger claim to feel inevitable, because the conformal boundary is meant to be more than a convenient approximation. It is meant to be a real bridge, a place where the notion of scale genuinely loses its grip. If mass remains in principle, the bridge becomes more fragile. Vacuum stability adds another uncertainty, and it is a reminder that cosmology depends on particle physics. Our vacuum might be metastable, meaning it is not the absolute lowest energy state. A decay could rewrite the far future, and it could do so abruptly, like a phase transition sweeping through space. A vacuum transition could end an aeon violently, preventing the quiet conformal boundary CCC requires. Or it could create a different kind of boundary, with different fields and different symmetry. CCC does not yet have a complete account of such events, because the relevant physics is not settled, so the bridge between aeons cannot be built from black holes alone, even if black holes provide the drama. It needs a geometric rule, something that tells spacetime how to connect one era to the next. Conformal matching is that rule, and it is the mathematical heart of CCC. Conformal matching proposes a way to glue the end of one aeon to the start of the next, without preserving ordinary distances. The key move is to rescale the metric, multiplying it by a conformal factor that can blow up or shrink lengths. Angles are preserved, and null directions are preserved, but rulers are not. Light cones remain unchanged under conformal rescaling, and that is the crucial invariant. Time-like and space-like intervals change, but causal structure persists. In plain language, the pattern of what can influence what remains the same, even as the meaning of how far is rewritten. In Penrose diagrams, infinity can be brought to a finite boundary, and the trick is not merely artistic. The infinite future becomes a surface, a line you can point to on a page, because the conformal factor compresses endless time into a finite coordinate range. This is how relativists make the global structure of spacetime visible. CCC identifies that surface with a new Big Bang, and the identification is bold. The next aeon begins where the previous aeon's conformal time ends, so the far future is reinterpreted as a kind of beginning. The boundary is not a place you could visit, but it is a place the mathematics can define. This is not a bounce in the usual sense, and CCC insists on that distinction. There is no contraction to high density in ordinary proper time, and no reversal of the expansion. Instead, the end is stretched and then squashed by a conformal factor, and the singularity is avoided by redefining scale. The mathematical elegance is clear, and it is part of the appeal. The physical meaning is the open question, because elegance does not guarantee reality. What does it mean to identify two manifolds across a boundary, and what does it mean for fields that live on those manifolds? What fields are continuous, and what data are reset? Are there matching conditions for radiation, for curvature, for quantum states? CCC claims the Weyl curvature can be controlled, and that the boundary condition can enforce low gravitational entropy at the next start. In CCC's language, the early universe is special because it is smooth in a gravitational sense. The Weyl tensor measures tidal distortion and free gravitational degrees of freedom, and low Weyl curvature corresponds to low gravitational entropy. The proposal is that the conformal boundary naturally sets Weyl curvature to zero or close to it, but the mechanism is not derived from a full quantum gravity theory. It is a proposal about how geometry should behave when scale loses meaning. That makes CCC both intriguing and vulnerable, because it lives where our current theories do not fully reach. This brings us to space-time geometry at extremes, where black holes and big bangs are the stress tests. Classical general relativity is extraordinarily successful, but it predicts its own breakdown in certain regimes. Those regimes are marked by singularities, and singularities are warnings that the theory is incomplete. Singularities appear in general relativity under broad conditions, as shown by the Penrose, Hawking singularity theorems. The theorems show geodesic incompleteness, not necessarily infinite density, and that distinction matters. It means space-time paths end prematurely, so the theory cannot tell you what happens next. Cosmic censorship is a hope, not a proven law, and it is a hope about what observers can see. It suggests singularities are hidden behind horizons, so the worst pathologies are not visible from the outside. If censorship holds, nature protects predictability by keeping naked singularities out of view. But CCC wants to avoid a classical singularity entirely, because it wants a clean boundary. In CCC, the Big Bang is not a conventional singularity, and it is not a place of infinite curvature. It is a conformal boundary where scale is redefined and where the geometry is continued in a different guise. Other cyclic models take different routes, and the comparison clarifies what CCC is and is not. Bouncing cosmologies use contraction, then a bounce from new physics, often invoking modifications to gravity at high density. Some use loop quantum cosmology effects, where quantized geometry can produce a repulsive term near Planck density. Some use ekpyrotic smoothing in a slow contraction phase, where an ultra-stiff equation of state suppresses anisotropies. Those models face their own entropy problems because they must prevent entropy from accumulating cycle after cycle. If each cycle inherits the mess of the previous one, the cycles degrade. CCC avoids that by not recycling matter, and that is a central conceptual move. It recycles only conformal geometry and radiation-like content, while matter in the usual sense is meant to fade away. The price is that CCC must explain why the boundary is physically allowed, not just mathematically writable. A mathematical identification is not automatically a dynamical process, and physics cares about dynamics. Something must enforce the matching, and something must explain why the universe chooses that route. Here the missing piece becomes unavoidable, and it is the same missing piece that haunts every extreme cosmology proposal. We do not have a complete theory of quantum gravity, and we do not have a universally accepted set of rules for Planck-scale spacetime. We can do semi-classical calculations, and Hawking radiation is the flagship example of controlled reasoning without full unification. That success is real, but it has boundaries. We can compute particle creation on a fixed background, and we can include back reaction approximately in limited regimes. We can track how energy loss changes the mass slowly, as long as the curvature remains small. But we cannot yet describe the Planck scale end of evaporation with confidence. We cannot yet describe the earliest moments with confidence either, because the same scales appear. CCC's handoff lives exactly in that gap, and it asks quantum gravity to permit a conformal transition without a singular crash. It asks for a graceful rule at the very edge of our competence. Some approaches hint at tools, and they are worth naming because they shape the modern landscape. Path integrals over geometries suggest that space-time history might be summed over, not fixed. Holographic dualities suggest that space-time might be encoded in a lower dimensional quantum system. Quantum error correction ideas suggest that bulk locality might be approximate, protected by redundancy and entanglement. These hints are not a finished theory, but they change what seems possible. They make it less absurd that a boundary condition could emerge from deeper quantum rules. But none provide a finished, universally accepted account of cosmological initial conditions. None yet derive CCC's matching as inevitable, rather than as an elegant option. So the chapter's climax is not a solution, and it should not pretend to be. It is a confrontation with what we do and do not know, and the confrontation has sharp edges. If black hole evaporation is unitary, the far future may retain hidden complexity and correlations. CCC must show why that complexity becomes irrelevant for conformal matching, not merely invisible to coarse measurements. If stable masses persist, conformal invariance may fail in principle. CCC must show why physics still forgets scale, and why the remaining mass scales do not obstruct the boundary. If vacuum decay occurs, the quiet boundary may never form, and CCC must show why our vacuum survives long enough. If quantum gravity resolves singularities differently, the bridge may look nothing like conformal matching. CCC must compete with other resolutions, and it must do so with predictions, not only with geometry. Now the comparison with inflation returns, because both stories claim to explain beginnings. Inflation adds a dynamical smoothing phase in the early universe, and it is designed to solve specific problems. It stretches quantum fluctuations into classical perturbations, and it drives regions of space toward flatness and homogeneity. In visual terms, it takes a tiny patch and balloons it into a cosmic canvas. Inflation often leads to a multiverse through eternal inflation, where inflation never ends everywhere. It produces pocket universes in an inflating background, each with its own reheating history. The multiverse here is branching, like bubbles forming in a boiling pot. CCC offers a different multiverse language, and the difference is structural. It offers sequential eons rather than branching bubbles, and it ties diversity to the long internal history of each aeon. Instead of many universes side by side, it imagines many universes one after another. Inflation's diversity comes from quantum branching in a potential landscape, and from different ways inflation can end. CCC's diversity comes from the accumulated astrophysics of an aeon, including black hole mergers and the distribution of mass and radiation. Both are speculative in parts, but they speculate in different directions. Their predictions differ in emphasis, and the differences are where evidence can bite. Inflation predicts specific statistical properties of primordial perturbations and possible primordial B-modes in polarization. CCC predicts possible imprints from prior eons and a different account of initial low-whale curvature. Both face contested evidence because the sky is subtle and the data are hard. Neither framework is free of untested assumptions, and neither should be treated as settled doctrine. Inflation assumes an inflaton sector and a reheating history, and CCC assumes conformal matching and an effectively massless far future. Both assume quantum gravity will not sabotage their core steps, and that assumption is the shared vulnerability. So we stand at a fork that may be false, because nature is not obliged to choose between our favourite stories. The real answer could be a third option not yet formulated, built from principles we have not discovered. At this point, the documentary's hook tightens. The end of the universe might be a thermodynamic fade or a geometric handoff. The visuals can linger on a cold, expanding cosmos, where galaxies have slipped beyond reach and only thin radiation remains. If CCC is right, black holes are not only tombs, they are the last scribes, writing energy into the boundary, and perhaps writing it in a way that can be read as structure in the next aeon. The idea is both haunting and precise, because it ties cosmic rebirth to a calculable quantum process. If CCC is wrong, the same physics still teaches something, and it teaches it sharply. It shows how close our theories come to contradiction at horizons, and how much of spacetime may be encoded in quantum information. The information problem is not a side plot, it is a clue about what spacetime is made of. Quantum gravity is not a missing chapter we can skip. It is the binding that decides whether any cyclic story is physical, and whether any boundary condition is more than a choice of coordinates. The bridge between aeons is not built from poetry, it is built from rules. So we end this chapter with the central question sharpened to a point. After heat death, does the universe truly end, or does geometry permit rebirth? We have reached the bridge, and the bridge is made of uncertainties, each one a test of our deepest assumptions. The final chapter must decide what counts as a scientific rebirth, rather than a metaphorical one. With the evidence contested and the theory incomplete, we return to the central question. What does it mean, scientifically, to say the universe rebirths after it ends? We return to the central question, now stripped of romance and defended by physics. After heat death, does the universe truly end? Or can geometry turn an ending into origin? The question sounds poetic, yet it is also technical, because it depends on what we mean by time, scale, and measurable change. Under standard cosmology, the long future is an asymptotic fade of structure. Expansion thins matter, redshifts radiation, and drives most regions beyond each other's horizons. Galaxies that are now neighbours drift apart until even their light can no longer reach us. On the larger scales, the sky grows emptier, not with a bang, but with a quiet loss of contact. In LCDM, accelerated expansion is not just motion through space. It is the stretching of spacetime itself, described by a scale factor that keeps growing. As that scale factor rises, wavelengths stretch with it, and energy densities dilute. Radiation cools faster than matter, and matter thins until interactions become vanishingly rare. Entropy rises, free energy vanishes, and the remaining dynamics become rare and increasingly unmeasurable. Stars burn out, then stellar remnants cool, and even the most stubborn structures erode. If protons decay, baryonic matter dissolves into light particles over immense timescales. If they do not, the story still trends toward isolation and exhaustion. Heat death is not a single event that happens on a date. It is a limit where gradients disappear and the probability of organized change approaches zero. Temperature differences flatten, chemical potentials equalize, and work becomes impossible in the everyday thermodynamic sense. In that limit, the universe does not explode or collapse. It simply stops offering new macroscopic stories. Visually, imagine a cosmic timeline that once bristled with landmarks. The era of recombination, the first stars, the rise of galaxies, and the brief flare of heavy elements. Then the marks thin out like ink running dry, until the page shows almost nothing but blank space. The physics is still there, but the events that make time feel eventful are gone. The earlier chapters pushed a sharper point beneath that quiet. If clocks and rulers require stable, massive systems, then measurement itself becomes fragile. A bath of long-wavelength radiation can exist, yet it cannot easily define duration without a counter. A clock is not merely a number, it is a physical process that repeats in a reliable way. In the early universe, clocks were abundant because matter was dense and interactions were frequent. In the far future, the opposite holds, and the operational meaning of time begins to fray. You can write down a time coordinate in equations, but you may not be able to build anything that experiences it in a structured way. The distinction is subtle, yet it matters when after becomes a question about what can be defined. That operational problem is not a loophole in thermodynamics, it is a statement about what physics can mean. Proper time belongs to time-like world lines, and massless quanta do not carry it. A photon has no rest frame, and along its path the interval is null. If only null trajectories remain, the word after becomes harder to anchor. Even the idea of a tick depends on scale. A second is defined through atomic transitions, and those transitions require bound states and mass. If the far future becomes dominated by radiation and effectively massless particles, the reference points that once set our units evaporate. What remains may still be describable, but it is no longer describable in the familiar way. This is where conformal cyclic cosmology makes its most audacious move. CCC says the far future may become effectively massless and therefore scale-free. If scale loses meaning, conformal geometry becomes the natural language of what remains. The proposal is not that matter survives forever, but that the geometry of light-like structure can outlast matter's ability to define size. Conformal transformations preserve light cones while discarding absolute size. They keep causal structure intact while allowing infinity to be compressed into a boundary. In practical terms, they preserve angles and the distinction between time-like, space-like, and null directions. They do not preserve distances, which is exactly the point when distances cease to be physically meaningful. CCC proposes that the remote future of one aeon can be conformally matched to the Big Bang of the next. The word matched here is careful, almost legalistic, because it is a statement about equivalence classes of metrics. You take a spacetime that has expanded without bound, rescale it, and ask whether its conformal structure can be smoothly continued. In Penrose's framing, the infinite future becomes a finite surface, an edge where one description hands off to another. In layered form, the answer becomes two answers that share the same starting facts. Standard cosmology says heat death is a true end of structure, even if time continues mathematically. CCC says the same end state might be redescribed as an origin, because only the light-like skeleton matters. The divergence is not about what happens next Tuesday, but about what end means when scale disappears. CCC does not claim a simple repeating timeline with identical histories. It does not promise that you, or Earth, or any galaxy returns. It claims a sequence of aeons connected by geometry, where time and scale are reinterpreted at the boundary. The repetition is not of events, but of a structural possibility, that a scale-free future can be read as a scale-free beginning. The bridge is not a physical tunnel carrying matter across. It is a matching of conformal structures, a rule about how one space-time description hands off to another. The continuity is in angles and null directions, not in objects and distances. What survives is not a cargo of particles, but a pattern of causal relationships. That distinction matters because it prevents a common misunderstanding. CCC is not a cosmic reset button that rewinds events. It is a proposal that the universe can forget scale so completely that the end can be identified with the beginning. Forgetting here is not psychological. It is the physical loss of any operational handle on absolute size. Historically, this idea sits in a long tradition of using geometry to tame infinities. In the 20th century, conformal diagrams became a standard tool in general relativity, letting physicists draw infinite regions on finite paper. Penrose's own work on singularities and gravitational collapse helped define what beginning and end mean in spacetime. CCC extends that geometric instinct into cosmology, with a claim that is bold precisely because it is so spare, yet the documentary's tension has never been only philosophical. CCC must face the same demand as any cosmology. It must make predictions that survive new data, not only offer a compelling reinterpretation of old mysteries. A beautiful boundary condition is not enough if the sky refuses to cooperate. We tested the most direct empirical arena, the cosmic microwave background. CCC-inspired searches look for localized imprints like Hawking points and for ring-like low-variance features. The idea is that violent events late in a previous aeon, especially supermassive black hole mergers, could leave faint circular signatures after conformal matching. Those claims remain disputed because significance depends on pipelines, masks, and look elsewhere accounting. The CMB can tell us about early conditions with extraordinary precision. It can also mislead us with foreground residuals and statistical flukes because we have only one sky. The map is a single realization of a random field, and cosmic variance limits what can be concluded at the largest angular scales. Intriguing anomalies are not decisive evidence, even when they are visually persuasive. In visuals, the temperature map looks like a mottled sphere, with hot and cold patches only tens of microkelvin apart. Overlay a mask, and the galactic plane becomes a missing strip, because dust and synchrotron glow drown out the primordial signal. Then change the processing choices and subtle rings can appear or vanish. The lesson is uncomfortable. The data are real, yet interpretation is fragile. Elegance is not evidence, and discomfort with inflation is not a detection of CCC. A theory earns belief by risking failure in ways that are unambiguous. The history of cosmology is a history of beautiful ideas being disciplined by error bars. Even the Big Bang model itself earned trust slowly, through multiple converging lines of observation. So we reconcile the philosophical and the empirical without flattening either. CCC is attractive because it reframes what an ending is, and because it targets the low-entropy puzzle. But the universe does not reward aesthetic coherence unless it also matches the data. In cosmology, the most seductive stories are often the ones that must be tested hardest. We can now say what would actually decide the question, at least in practice. The first decisive tests are next-generation CMB polarization maps with lower noise and better control of systematics. Polarization adds independent structure that can confirm or break temperature-only anomalies. It also carries information about scattering at recombination, which is sensitive to early universe conditions. Polarization is not just a technical upgrade, it is a different kind of evidence. The E-mode pattern is now measured well, and it matches LCDM with striking fidelity. The B-mode pattern is far harder, because it is weaker and easily contaminated. If primordial B-modes were detected robustly, they would strongly favour inflationary gravitational waves. Better foreground modelling is not a technical footnote, it is a gatekeeper. Dust polarization, synchrotron complexity, and spatially varying spectra can mimic subtle features. A CCC signal must persist across frequencies, component separation methods, and independent instruments. If it appears only in one band or one pipeline, it is not a cosmological relic. We also need improved statistics for large-scale anomalies. Low multipoles are cosmic variance dominated, so claims must be framed with rigorous null tests and pre-registered pipelines. The goal is not to collect oddities, it is to compare models with honest trial counting. When you search many patterns, some will look special by chance, and that fact must be priced in. Independent probes of early universe physics can also separate stories that look similar in temperature maps. Primordial gravitational waves, if detected, would strongly support inflationary dynamics. Tight upper limits already constrain many inflation models, and they also constrain alternatives. The absence of a signal is not nothing. It reshapes the space of viable beginnings. Large-scale structure, lensing, and spectral distortions provide additional cross-checks. A model that changes initial conditions must still reproduce BAO, matter clustering, and CMB lensing statistics. The web of galaxies is not merely scenery, it is a fossil of primordial fluctuations. Cosmology advances when one explanation survives many linked datasets. The theoretical side has its own decisive bottlenecks. CCC depends on the far future becoming effectively massless, so conformal invariance is not merely approximate. Stable massive particles, neutrino masses, or long-lived dark matter could obstruct that limit in principle. If rest mass never truly disappears, then scale may never fully lose its meaning. This is why CCC often emphasizes a kind of ultimate simplification. In the deep future, black holes dominate as reservoirs of mass and entropy, while everything else becomes dilute. Then Hawking evaporation, over fantastically long times, removes horizons and returns energy to radiation. In Penrose's framing, the evaporation era is a cosmic laundering of structure, an erasure of the last clumps. CCC also leans on black holes as the last major reservoirs of gravitational entropy. Hawking evaporation removes horizons and can, in Penrose's framing, erase gravitational clumping. But modern work on unitarity suggests evaporation may preserve information in correlations, not destroy it. The radiation may look thermal locally, yet still encodes subtle quantum structure globally. That creates a subtle tension that cannot be waved away. If information is preserved, the far future may be thermally simple, yet quantum mechanically intricate. CCC must explain why that hidden complexity does not reintroduce gravitational entropy at the conformal boundary. The question is not whether the universe is cold, but whether it is truly forgetful. We return to entropy in the arrow of time, because every origin story must face it. The second law explains why macroscopic time has a direction once low entropy is given. The deeper question is why the early universe had low gravitational entropy at all. In gravity, smoothness is special, because clumping is the generic direction of evolution. Penrose framed this in terms of Weyl curvature, the part of spacetime curvature associated with tidal distortion and gravitational radiation. A nearly uniform early universe has low Weyl curvature, which means it is gravitationally ordered in a precise sense. Later, as structure forms and black holes appear, gravitational entropy rises dramatically. The arrow of time is written into the geometry, not only into the temperature. Inflation can smooth and dilute, but it does not automatically explain why the inflating patch was special. It can take a small, smooth region and stretch it, turning microscopic uniformity into cosmic uniformity. Yet it still requires conditions that allow inflation to start, and it raises measure questions about what typical means. CCC proposes a boundary condition that enforces low Weyl curvature at each new beginning. That can look like an explanation, or like relocating the mystery into the rules of matching. If the conformal boundary naturally suppresses Weyl curvature, CCC may explain the smooth start without fine-tuning. If that suppression is assumed rather than derived, the low-entropy puzzle remains, only reframed. The difference between derived and imposed is the difference between mechanism and declaration. Dark energy and horizons also return as a constraint on what after can mean. Accelerated expansion fractures the universe into causally isolated regions, so no global dynamical reset can sweep through. CCC's handoff must therefore be geometric, not a signal travelling through space. The universe cannot pass a message across an event horizon, yet a conformal identification does not need to. That is both a strength and a vulnerability. It avoids the need for matter to cross horizons, because horizons are irrelevant to conformal identification. But it also means the proposal lives at the level of spacetime description, where empirical access is indirect. We are testing a boundary with relic patterns, not watching a transition unfold. At this point, the documentary does not pretend to settle the debate by narration alone. Under standard LCDM, heat death is the asymptotic end of structure and of meaningful measurement. Under CCC, the same future could be conformally equivalent to a new Big Bang, turning an end into a boundary. The difference is not a minor tweak, it is a different reading of what counts as physical continuity. The honest conclusion is that both pictures are currently underdetermined by the evidence. CCC is not ruled out, but its claimed CMB signatures are not yet robust. Inflation is not disproven, but its microphysics and measure problems remain open. In the background, the data keep tightening, and theories keep being forced into sharper commitments. So we end by clarifying what the series has actually learned. The universe forces us to separate three ideas that we often blend: physical time, operational time, and narrative time are not the same thing in the deep future. When the universe thins out, those distinctions stop being academic. Physical time may continue as a parameter in equations even when nothing changes. Operational time may fail when no clocks can exist and no scales can be compared. Narrative time ends when the universe can no longer support new, recorded differences. The last of these is the one our intuitions cling to, because it is the one that feels like living. CCC exploits that separation in a precise way. If operational scale fades, then conformal geometry can become the only surviving structure. In that regime, the distinction between infinitely late and infinitesimally early can blur, because both are scale-free. The boundary is not a place you travel to, it is a description you arrive at when size stops mattering. Even if CCC is wrong, that lesson remains. The end of the universe is not necessarily a catastrophe, it may be a loss of distinguishability. The deepest future may be simple enough that our usual categories stop applying cleanly. When everything's the same temperature and nothing can form a clock, later becomes a word without a job. We bring the focus back to the human scale without shrinking the science. We're a brief pattern in a long thermodynamic story, built from gradients that will not last. Our bodies, our machines, and our memories all depend on differences, hot and cold, high and low, before and after. The universe gave us those differences for a while, and we learned to read them. Yet we can read origins from faint light, and that ability is itself a cosmic fact. A microwave photon that last scattered when the universe was young can still reach a detector built by creatures on a small planet. That chain of causality is astonishingly long, and it is also fragile. It depends on expansion, transparency, and the persistence of physical law. Cosmology is the art of extracting beginnings from relics that barely reach us. It turns microwaves into parameters, and parameters into histories. It also teaches humility, because one sky must answer questions that feel larger than any dataset. We do not get to rerun the universe, we only get to measure it more carefully. So what happens after the universe ends? In the standard view, the answer is that nothing happens in any meaningful macroscopic sense, because structure and measurement asymptote away. In CCC, the answer is that the far future might be the next beginning, because scale is no longer physical. The same mathematics of expansion can be read as a final dilution, or as a geometric handoff. We close on the only ending that is faithful to the evidence and to the mystery. The last photons of a dying cosmos may be the first light of another, if not in reality, then in the way physics reshapes the word end. On screen, the final glow fades toward darkness, then resolves into a new horizon, sharp, bright and unfamiliar. The page turns, and the question remains disciplined by what the sky will allow us to claim. We followed the universe as it spends its last reserves of difference, burning stars into embers, embers into remnants, and remnants into horizons. We watched entropy rise not as a villain, but as statistics made cosmic, free energy thinning, islands of causality drifting apart and black holes briefly becoming the final engines. Then even those engines fade, and the story turns stranger, because when only radiation remains, clocks and rulers lose their grip, and time becomes a question instead of a backdrop. In that deep future we met the central tension, between a one-way heat death and Penrose's conformal cyclic cosmology, where a scale-free end can be rewritten as a beginning. We tested the poetry against the data, asking whether the microwave sky carries scars of earlier aeons, or only the familiar fingerprints of inflation and chance. And we faced the hardest bridge of all, where Hawking evaporation meets quantum gravity, and where information may be preserved as hidden correlation rather than erased into simplicity. Across every chapter, the same theme kept returning. Mass gives the universe its measures, and without measures, after may be a word with nothing left to anchor it. So what happens after the universe ends, after the whisper has finished and light has nowhere left to go? The most honest answer is that after might not exist in any operational sense, yet geometry could still connect what looks like an ending to what we call a first dawn. If CCC is right, the universe does not reboot by recycling matter. It turns a boundary into a birth by letting scale evaporate, until only light cones remain to carry continuity. If CCC is wrong, it still leaves us with the haunting lesson that cosmological endings may be transformations of description. When the final darkness arrives, it may be the moment the page turns. Watch the next maps of the microwave sky, demand careful statistics and open pipelines, because the decision may come not from philosophy, but from a faint pattern in ancient light.